It's not necessarily going to be it wouldn't be a minute for minute slip. And so that's kind of why we want to let the team work through it. They didn't reset the clock until, the T-minus 40-minute hold time frame there yesterday. So there's not a lot of margin in the timeline. It's very orchestrated, but they may be able to deal with certain, 15-minute delays, 20-minute delays, those sorts of things. And we'll try and make up time as they go through. But I would just say there's not a lot of margin in that timeline.
Okay, I'll take the next question here.
Stephen Young with Spaceflight Now for Jeremy. After the WDR, you extended some holds to get a little more padding in the schedule, and you've done that again to get the engine bleed kickstart work in and pressurize the tank, etc. I'm just wondering if you could give us an idea about the length of the workday for the launch team. When people come in, is it multiple shifts? How does that work? And are there any post-launch traditions that we should expect to see? Will there be beans and maybe a pair of scissors involved?
Great question, and really appreciate that. So we're watching the team really closely. It's not one size fits all, right? So some systems, it may be a couple of different folks going through. When you look at some of the leadership, like Charlie or some of our integration console, they're playing for about 12-hour days. Is really kind of what we're going into right now. If we get into a scrub or at the end of the window, it could go a little bit longer than that. But in general, kind of what we're saying is, 12-hour days is what we're really scheduling them for. We've really been watching the team closely. For example, I'm here this morning so we can give Charlie the morning off, right? And some of the key test conductors and test directors. And so we're just really kind of focused on them. We're talking to them. We're making sure that they feel good and healthy kind of going into tomorrow's attempt and are rested. When you talk about what are some of the celebrations, so we will have beans and cornbread in the Launch Control Center afterwards. And the integration console has all asked Miss Blackwell Thompson to cut their ties afterwards. So pretty excited to see those things. We're also trying to establish a few of our own traditions. And so what you'll see is I'll definitely be wearing a green tie for launch day to show solidarity with some of our launch director and some of the others there.
Thank you for that question. Over here.
Jim McDade, 1819 News. Melanie, could you please give us an overview of the Anvil cloud rule? And so I think a lot of our readers would like to know more about that.
Okay. Essentially, I can tell you what the rule is based on, and I can kind of give you an overview of why some of our rules exist at all. So primarily, our rules exist because based on two principles. Number one, you can't fly into an active thunderstorm, right? And then number two, you cannot trigger your own lightning strike. And we've seen that in the past at least twice. So basically, if you think about it, we're sending a charged rod up into the sky. We've done half the work for the atmosphere already. So the Anvil rule is just kind of a continuation of that, where basically it's a spread of the electric current possibly along the Anvil, extending farther away from the parent thunderstorm. So because of some of that electric current could still exist, and sometimes it is masked by the outside of the cloud, we don't have a good handle on how to see it and how to read it. So it's just a built-in conservatism into the rule to make sure we don't trigger our own lightning strike.
Okay, we'll go to the phones and then we'll come back here to the room. I see the two hands in the front row. On the phone, we have Bill Harwood, CBS News.
Yeah, hi, thanks, Jeremy. I don't know if you can answer this question or not, but you got 46 colas for this launch, and I realize that going up to apogee and then back down to perigee for TLI, you're passing through, multiple realms of satellites. But any idea how Starlink plays into all of that, if it does at all? Thanks.
Let's see, Bill. So honestly, the Space Force does that analysis for us. When we look at it, we got about, like you said, about 45 cutouts. Many are short in duration, typically, a couple of seconds each, with about 10 of them being about a minute each. In terms of what kind of goes behind that analysis, I honestly don't have the answer for you there. It is a mix of satellite position, orbital debris, and things like that. But honestly, the Space Force kind of looks at the specifics with whether it's Starlink or other things along those lines.
Another one from the phone real quick. Kristen Fisher, CNN. Kristen, are you there?
Oh, sorry, guys. Sorry. It took me a minute to get off hold. My apologies. just wondering if it would be possible to get a update on exactly what the new duration of this mission is going to be. I believe Mike Serafin said yesterday 37 days, but some of our folks at CNN were trying to do the math and we weren't quite seeing it add up. So could we just get an update on, I believe the first launch attempt, it would have been 42 days. If it goes on Saturday, how long will the mission be? Thank you.
Yeah, so as you started kind of doing the count, I think a couple of the things that are relevant there is, do you count the launch day? And so essentially that's probably where you're kind of getting a couple of different durations. And then we're also just a couple hours shy of 38 days, I believe. Right now, if we launch tomorrow afternoon, we would land on October 11th at 11:10 Pacific time. So so that kind of gives you the duration. And, you know, what we would say is it's approximately 37 days to 38 days, depending on kind of where you choose to draw those lines.
Thank you, Jeremy. Okay, here.
Smith, spacepolicyonline.com. If you do have to scrub tomorrow, I gather you've got Monday and Tuesday as possibilities. Is that the end? I mean, at that point, do you have to roll back to the VAB because of replacing the battery in the flight termination system, or are you negotiating with the range to see if they could extend that some more, or do you absolutely positively have to go back to the VAB?
Yes, ma'am. It's a good question. So right now, it's our flight termination system is the kind of the pacing function for needing to roll back after this launch period. And what it is it's based off retest requirements. So right now, the range says every so many days you need to prior to launch, you have to test that flight termination system. Right now, we worked with them. We provided data for a little over 20 days since we tested it to launch time. We believe we would need to roll back and retest that system just to meet the range requirements. So right now, after 9/6, we'd roll back, retest. We don't actually have to replace the batteries until the next launch period, but it's a relatively short retest of the flight termination system just to provide confidence to the range that, you know, the public will be safe.
Follow up, will you be able to recharge the batteries on the 5 accessible CubeSats while you're back in the VAB?
So I honestly, I can follow up with you on that one. Typically, what we would do is during power up, we're able to recharge, make sure everything's very good. A number of those will actually be charged up on orbit as well, but I can get you a specific answer on that one because I'm not positive.
All right, the front row here.
Thank you, Tarek Malik with the space.com for Jeremy. You mentioned that there's a possibility of catching up and making up time if you do get delayed on taking it. I'm just curious, where are the windows to do that? Is it just opening the hoses on the fuel line faster to fill or coming out of holds earlier? And how do you make that decision? Thanks.
So there's a couple of built-in holds throughout the timeline. I mean, there's activities throughout all of that. And so if, for example, we get to chill down a little bit quicker than expected or to the 100% filled on the tank and go into replenish. Again, it's minutes that you can make up in a number of those things, but there is not much padding in the timeline. What you saw on the first attempt was, you know, we were probably an hour down due to weather. And as we kind of progressed through the first 4 to 5 hours, you know, we had maybe made up 10 to 15 minutes, that sort of thing. So really it depends on, you know, speed, rate of chill downs. They're not going to change valve positions or anything like that.
We have a question in the third row over here.
Hi. Thanks very much. Trust your arms. Irene Klaus with Aviation Week. I have 2 questions. The first is, were there any other changes made that would cover the last 29 seconds of the countdown that, of course, were not done in the wet dress, but were practiced in the green run based on what you've learned with the sensor configurations and the LH2 flow? That's one question, just kind of to take us through the last 29 seconds of the countdown that haven't been tested yet, and if there's any changes in the process. And then the other question is about the COLAs. How are those accounted for in the countdown? Does Charlie call a hold, or will it be automatically, would the countdown clocks automatically stop, especially if you're already in a termination mode, or would you not pick up the final section of the countdown if there is one of these COLAs in that process? Thanks.
Yeah, no worries. So for the last 29 seconds, no changes were made. Really, in order to kind of maybe get at the base of your question, which was, what did we do to kind of mimic some of the green run activities? That's primarily where we intend to begin the kickstart test. And so that's happening before we get to stable replenish on the LH2 tank. And so we're bringing that much earlier into the flow and before we actually even get the hydrogen tank full. And so that really mimics exactly what we did out at Green Run. As far as when we go into the last 29 seconds and ALS handover, no changes were made based off that. And so a lot of this is a vestige of not getting all of those objectives bought off during wet dress rehearsal 4, and then really wanting to make sure we have strong process control. Let's see, I'm sorry, can you repeat? Okay, so the COLAs, how do we account for that? Thank you for the reminder. So on that one, it really will depend on when we choose to reset the clock. So say we go in, what happens right now is the GLS integration console. So our ground launch sequencer has a series of times of when those cutouts are. And so if we run into any issues, what we'll do is we'll perform an analysis and say, we are good to launch at X time, and they'll reset to that, and then they avoid the COLA. So it's not completely automated, but we do have folks that have those times up, and it's really when we go about resyncing the clock to a new T0 time.
Thanks.
Thank you. Kenneth?
Yeah, hi, Ken Chan, New York Times. So in the last couple of days, we've heard a lot about the hydrogen line bleed kickstart. I was just, and that's to sort of verify your procedures. I was wondering, once that all sorted out, in a normal countdown, when does the engine chill down occur?
Okay, so let me try and get to the core of your question. So when do we kind of, maybe I'll repeat it back. So when do we validate our new procedures? Is that the question?
No, assuming everything works the way you want it to this time. So for Artemis 2, when would the chill down actually occur during a normal countdown?
Sorry about that. So the kickstart procedure is something that I do think we will do every single flow. And so we'll know that relatively early on. What we are doing this time around that we would not necessarily add into future tests is a pre-press test. And that's just us kind of getting into understanding exactly what the controls are, how everything's behaving. And that's really going to be a risk mitigation to the terminal count. But I do believe we will not continue to do, or we will do the kickstart similar in every single flow.
And what time in the countdown would that occur later?
So right now it's going to occur at approximately 8 a.m. I don't have the T-minus time right on me, but it should occur about 8 a.m. for about an hour.
No, in the future.
It would be at a similar time.
Okay, thanks.
We have some questions on the phone. We have Jim Siegel, NASATech.net.
Oh, thank you for taking my question. If the launch moves to Monday instead of Saturday, when will the launch window open? And I assume that it'll still be a 2-hour launch window. Thank you.
Let's see. So our launch window opens, it's a couple hours later. I don't have that exact information with me handy, so I'll have to get back to you exactly at that time. And so I'll just follow up if you don't mind.
Yeah, absolutely. Jim will get back to you on that one. And then we have Anthony with main engine cutoff on the phone.
Hey there, thanks for taking the call. For Jeremy, if the crack on the core stage foam yesterday was mentioned that that's not an issue for flight, are there any other areas on the core stage where that would be an issue, and how are those monitored?
So we do a series of checks throughout launch countdown and actually in between the last attempt and this one where we go through, we do thorough inspections of the vehicle. Even very minor defects are noted. Throughout launch countdown, we have a team which we call CICE on the console, and they do inspections throughout. So they use high definition cameras, infrared, things along those lines. And so right now we've done a full inspection of the vehicle. We've noted any nonconformances, and they've cleared any of those for flight. Throughout the count, as we see cryo pumping, things like that, we're going to continue to do the same thing. If anything is anomalous, they note it, and then they turn it over to a debris trajectory analysis team to decide whether or not we have any concerns. So they have standards that they use against, and they have models that we run it if it's above those standards. And then just to answer the other question, it was 5:17 p.m. is the launch time, and I believe it is a 2-hour window as well.
5:12, actually. 5:12 on the, yep. Nope, it's okay. It's 2:17 Saturday. So 5:12 on Monday, no problem, with that 90-minute window to answer Jim's question from before. Somebody had a question in the room here? Yep.
Aaron Cooper with CNN. Knowing everything you know, can you kind of bottom line it for us? How confident are you that this is going to fly on Saturday? How confident are you it's going to fly before the end of the Tuesday windows?
Yeah, so this is a test flight, right? And so while I feel very good about our procedures, when you look the team in the eye, they're ready. We can't control the weather. And so on any given day, there is risk that we'll be able to get off. I think what I kind of am looking at is our team is ready. They are getting better with every attempt and actually performed superbly during launch countdown number 1. So in my mind, I think if the conditions with weather and the hardware align, we'll absolutely go. And we have the right team at kind of the right time. So, and those statistics, right, those probabilities go way up if we get 2 attempts off before the end of this window.
And I believe there was another one in the room. Was there another hand in the room? No? Oh, over here.
Hi, I'm Brandy Campbell with Fox Weather. With the weather being favorable at 60%, how often have you guys had a successful launch at that, I guess, rate? And with that being the rate, I guess, do you foresee us maybe waiting a while for like a good time to take off, or is there a chance we could take off, at the beginning of the window?
Those are excellent questions. I don't have the exact stats that you're searching for. I can get back to you with that. I can tell you, though, that on any given day, there's about a 1 in 3 chance that we will scrub for any reason. And out of those chances of us scrubbing, there's a 50% chance that it's due to weather. So hopefully that's some stat you can take back. Could you remind me of the second part of your question?
Yes, I was asking, is there a chance that we might have to wait a while for there to be a good opportunity for us to launch throughout that weather, being that it's a 60% chance favorable?
It's entirely possible, and that's why I trended the forecast as such. I did today, making it worse at the beginning of the window and a little bit more favorable at the end. It really all depends on that sea breeze and whether it moves inland as fast as we are expecting. If we are looking at the balloon data in the morning and that easterly flow is not nearly as established as we were hoping to see, we could run into a situation where we're red a little bit longer than we expect to be. But overall, that sea breeze does tend to win out with easterly flow, regardless of truly how strong it is.
Okay, we don't have any other questions on the phone. If we're done here in the room, then I think we can wrap up today's news conference. Again, thank you, Jeremy, Melody, and everyone who asked questions. For more information on Artemis 1, we're going to pull up some resources here on the screen. You can take a look at this website. Also follow us on the social media channels you see there. Coverage of us tanking our moon rocket will begin at 5:45 a.m. Eastern Time tomorrow on NASA TV. And then our live launch coverage will begin at 12:15 p.m. For our Spanish viewers, our Spanish launch broadcast will begin at 1 p.m. We hope you can join us. Thanks so much. We are about 29 hours until our earliest opportunity to launch our Space Launch System and Orion spacecraft. You see them live there on Launch Pad 39B here at Kennedy Space Center. When it launches, Artemis 1 will be humanity's return to the moon in almost 50 years. Good morning and welcome back for another live briefing of our Artemis 1 mission. I'm Megan Cruz, and thank you so much for being here with us today. This briefing is to update you all on how our countdown is going so far. As you know, the 2-hour launch window opens tomorrow, September 3rd at 2:17 p.m. Eastern Time. Here to take your questions today are Jeremy Parsons, Deputy Manager of Exploration Ground Systems here at Kennedy. And then we also again have Melody Levin, a Launch Weather Officer with the U.S. Space Force. Good morning to you both. We will take opening remarks. Jeremy, let's start with you.
Good morning, and really appreciate everyone coming out today. Team is doing an absolutely tremendous job moving through launch countdown. And so yesterday at 14:17 local time, we reset the clock to T-minus 45 hours and counting. And so far, they're proceeding right on schedule. Last night, after the briefing, we powered up Orion. We performed all the RF testing. We also powered up the core stage. All looked nominal. We ran final leak checks on the inner tank umbilical. So this was the area that had a leak during launch countdown event 1. Again, all passed ambient along with the tail service mast umbilicals. So good leak checks there. And then yesterday evening, we also completed removing access stands and begin really final launch preps for the umbilicals. What we have on our plate today is a series of launch release system checks. We're charging the batteries on the flight elements, finishing final walkdowns, everyone kind of going through their systems, making sure everything looks and is in the appropriate configuration. We got a really busy afternoon, moving everything into final launch configurations. That's handrails, heavy equipment, things like that. When we talk about going into tomorrow and the day of launch, activities pick up really early. So at 2 a.m., we're doing full clearing of the blast danger area. We get into air to GN2 switch over at about 3:30 a.m. And so that allows us to then go into what we have is called a tanking meeting at 4:45 a.m. And we expect to get a decision coming out of there to where we can begin cryo operations at about 5:30. At 8 a.m., you'll expect to get into the engine bleed kickstart. So that's going to be one of those big milestones, again, that we're going to pay attention to. That will go on for about an hour. And afterwards, we'll be into replenish in terms of our commodities at that point for liquid hydrogen. When we get into after that, we have a pre-press test at T-minus 2 hours and 20 minutes. And so that'll be bringing the tank up to flight pressure for a period of time. That's really a risk mitigation for when we get into terminal count, so we don't run into any unexpected issues there. And then right now we're on track for a 2:17 p.m. launch. We have a 2-hour window. And so right now, team has really just done a fantastic job getting us out of launch attempt number 1, repairing all the issues, and getting us into a safe configuration to proceed into tomorrow's launch attempt. With that, that's kind of the quick update. Melody, you want to go through the weather, please?
Absolutely. Good morning, everyone. So the weather continues to still look pretty good for the launch attempt on Saturday. The flow has become onshore this morning, so let's go ahead and look at satellite, and so we can go ahead and talk about what's happening right now. And as satellites being pulled up, you can see there's actually a very weak trough positioned off to our north. And if you're able to focus your eyes just north of the Space Coast, you can see some thunderstorms forming close to Daytona this morning. Basically, that's indicative of onshore flow starting up. And we did see that with our morning weather balloon that was put up in the air earlier this morning. So with that onshore flow regime starting, it should strengthen as we get into Saturday, and that will likely do us some favors as we get into the later portion of the launch window Saturday afternoon. Again, we are expecting our weather to start off a little bit dicey as we get into the 11 o'clock, 12 o'clock time frame. So we'll go ahead and, since I'm already talking about the launch window weather, we'll go ahead and flip to that next slide of looking at that. So our weather is going to start off at a 40% probability of violation, which of course means a 60% go. However, we do start evaluating the weather 3 hours before the launch window opens. So of course, that's right around 11 o'clock or so. So I do expect to make some no-go calls at some point tomorrow. However, as that East Coast sea breeze drifts farther inland, we do expect clearing on the back side of that. And that is because that is the reason why we are trending the forecast to more of an 80% favorability at the end of the launch window tomorrow afternoon. So now we can go ahead and flip to the backup forecast, and that is on Monday afternoon and evening timeframe. I have the same numbers that I gave you yesterday, basically a 70% probability of go. However, there's a little bit more uncertainty in this forecast than what we had before. Previously, it did seem like we'd have a pretty steady easterly flow. At this point in time, it does seem like we're going to have a ridge right on top of us in the mid-level layers of the atmosphere. And because of that, it's kind of splicing the flow a little bit more than we expected. To the north of us, we're expecting more on the side of westerly flow, and to the south of us, we're expecting easterly flow. So of course, we're smack dab in the middle there, and that gives us a very, very light flow regime, and it could almost go either way. So with a forecast like that, basically we're going to be focused on the weather with those inland sea breeze boundaries. And sometimes with that kind of situation, we can see some anvils floating back towards us in general in the late afternoon and evening timeframes. So because of that, I did go ahead and add the anvil rule into the backup launch window. But in any case, like I said yesterday, I do not expect weather to be a showstopper by any means for either launch window.
Perfect. Thank you, Melody. All right. So for the reporters in the room, just raise your hand. We'll get a mic to you. And then for those on the phone, just press *1 to get into the question queue. I saw the first hand over here, Marcia.
Marcia Dunn, Associated Press. For Melody, what's the tanking forecast look like? Because we had a 1-hour delay on Monday before they could even fuel. And my other question for Jeremy is, if you have to delay the start of fueling for weather or for any other reason, is it a minute for minute slip in terms of what it does to the launch time, and how's that, or can you make stuff up as you do other things?
Okay, so of course I'll take that first question. Yeah, I'm glad you brought that up. Because we have onshore flow, we could have some showers approaching the coastline, and maybe a crack of thunder and lightning with that. So that is certainly a threat, again, a very similar threat to what we had the other day. The one difference, though, is we're not nearly as moist throughout the atmospheric column as we were the other day. So that's on our side. But it's very hard to predict shower activity offshore during the late night timeframes. It's much easier to predict the onset of the sea breeze than the approaching nocturnal showers. So it's possible that that could be a hindrance, but if we can get past that, I'm pretty confident that weather will be able to press forward for us.
Yeah, and to address your second question, so it's not necessarily going to be it wouldn't be a minute for minute slip. And so that's kind of why we want to let the team work through it. They didn't reset the clock until, the T-minus 40-minute hold time frame there yesterday. So there's not a lot of margin in the timeline. It's very orchestrated, but they may be able to deal with certain, 15-minute delays, 20-minute delays, those sorts of things. And we'll try and make up time as they go through. But I would just say there's not a lot of margin in that timeline.
Okay, I'll take the next question here.
Stephen Young with Spaceflight Now for Jeremy. After the WDR, you extended some holds to get a little more padding in the schedule, and you've done that again to get the engine bleed, kickstart, work in, and pressurize the tank, etc. I'm just wondering if you could give us an idea about the length of the workday for the launch team. When people come in, is it multiple shifts? How does that work? And are there any post-launch traditions that we should expect to see? Will there be beans and maybe a pair of scissors involved?
Great question, and really appreciate that. So we're watching the team really closely. It's not one size fits all, right? So some systems, it may be a couple of different folks going through. When you look at some of the leadership, like Charlie or some of our integration console, they're playing for about 12-hour days. Is really kind of what we're going into right now. If we get into a scrub or at the end of the window, it could go a little bit longer than that. But in general, kind of what we're saying is, 12-hour days is what we're really scheduling them for. We've really been watching the team closely. For example, I'm here this morning so we can give Charlie the morning off, right? And some of the key test conductors and test directors. And so we're just really kind of focused on them. We're talking to them. We're making sure that they feel good and healthy kind of going into tomorrow's attempt and are rested. When you talk about what are some of the celebrations, so we will have beans and cornbread in the Launch Control Center afterwards. And the integration console has all asked Miss Blackwell Thompson to cut their ties afterwards. So pretty excited to see those things. We're also trying to establish a few of our own traditions. And so what you'll see is I'll definitely be wearing a green tie for launch day to show solidarity with some of our launch director and some of the others there.
Thank you for that question. Over here.
Date 1819 News. Melanie, could you please give us an overview of the Anvil cloud rule? And yeah, so I think a lot of our readers would like to know more about that.
Okay. Essentially, I can tell you what the rule is based on, and I can kind of give you an overview of why some of our rules exist at all. So primarily, our rules exist because based on two principles. Number one, you can't fly into an active thunderstorm, right? And then number two, you cannot trigger your own lightning strike. And we've seen that in the past at least twice. So basically, if you think about it, we're sending a charged rod up into the sky. We've done half the work for the atmosphere already. So the Anvil rule is just kind of a continuation of that, where basically it's a spread of the electric current possibly along the anvil, extending farther away from the parent thunderstorm. So because of some of that electric current could still exist, and sometimes it is masked by the outside of the cloud, we don't have a good handle on how to see it and how to read it. So it's just a built-in conservatism into the rule to make sure we don't trigger our own lightning strike.
Okay, we'll go to the phones and then we'll come back here to the room. I see the two hands in the front row. On the phone, we have Bill Harwood, CBS News.
Yeah, hi. Thanks, Jeremy. I don't know if you can answer this question or not, but you got 46 colas for this launch, and I realize that going up to apogee and then back down to perigee for TLI, you're passing through, multiple realms of satellites. But any idea how Starlink plays into all of that, if it does at all? Thanks.
Let's see, Bill. So honestly, the Space Force does that analysis for us. When we look at it, we got about, like you said, about 45 cutouts. Many are short in duration, typically, a couple of seconds each, with about 10 of them being about a minute each. In terms of what kind of goes behind that analysis, I honestly don't have the answer for you there. It is a mix of satellite position, orbital debris, and things like that. But honestly, the Space Force kind of looks at the specifics with whether it's Starlink or other things along those lines.
Another one from the phone real quick, Kristen Fisher, CNN. Kristen, are you there?
Oh, sorry, guys. Sorry. It took me a minute to get off hold. My apologies. Just wondering if it would be possible to get a update on exactly what the new duration of this mission is going to be. I believe Mike Serafin said yesterday, 37 days. But some of our folks at CNN were trying to do the math and we weren't quite seeing it add up. So could we just get an update on, I believe the first launch attempt, it would have been 42 days. If it goes on Saturday, how long will the mission be? Thank you.
Yeah, so as you started kind of doing the count, I think a couple of the things that are relevant there is, do you count the launch day? And so essentially that's probably where you're kind of getting a couple of different durations. And then we're also just a couple hours shy of 38 days, I believe. Right now, if we launch tomorrow afternoon, we would land on October 11th at 11:10 Pacific time. So so that kind of gives you the duration. And, what we would say is it's approximately 37 days to 38 days, depending on kind of where you choose to draw those lines.
Thank you, Jeremy. Okay, here.
Smith, spacepolicyonline.com. If you do have to scrub tomorrow, I gather you've got Monday and Tuesday as possibilities. Is that the end? I mean, at that point, do you have to roll back to the VAB because of replacing the battery in the flight termination system, or are you negotiating with the range to see if they could extend that some more, or do you absolutely positively have to go back to the VAB?
Yes, ma'am. It's a good question. So right now, it's our flight termination system is the kind of the pacing function for needing to roll back after this launch period. And what it is it's based off retest requirements. So right now, the range says every so many days you need to prior to launch, you have to test that flight termination system. Right now, we worked with them. We provided data for a little over 20 days since we tested it to launch time. We believe we would need to roll back and retest that system just to meet the range requirements. So right now, after 9/6, we'd roll back, retest. We don't actually have to replace the batteries until the next launch period, but it's a relatively short retest of the flight termination system just to provide confidence to the range that the public will be safe.
Follow up, will you be able to recharge the batteries on the 5 accessible CubeSats while you're back in the VAB?
So I honestly, I can follow up with you on that one. Typically, what we would do is during power up, we're able to recharge, make sure everything's very good. A number of those will actually be charged up on orbit as well, but I can get you a specific answer on that one because I'm not positive.
All right, the front row here.
Thank you, Tarek Malik with the space.com for Jeremy. You mentioned that there's a possibility of catching up and making up time if you do get delayed on taking. And I'm just curious, where are the windows to do that? Is it just opening the hoses on the fuel line faster to fill or coming out of holds earlier? And how do you make that decision? Thanks.
So there's a couple of built-in holds throughout the timeline. I mean, there's activities throughout all of that. And so if, for example, we get to chill down a little bit quicker than expected or to the 100% filled on the tank and go into replenish. Again, it's minutes that you can make up in a number of those things, but there is not much padding in the timeline. What you saw on the first attempt was, we were probably an hour down due to weather. And as we kind of progressed through the first 4 to 5 hours, we had maybe made up 10 to 15 minutes, that sort of thing. So really it depends on, speed, rate of chill downs. They're not going to change valve positions or anything like that.
We have a question in the third row over here.
Hi. Thanks very much. Test your arms. Irene Klaus with Aviation Week. I have 2 questions. The first is, were there any other changes made that would cover the last 29 seconds of the countdown that, of course, were not done in the wet dress, but were practiced in the green run based on what you've learned with the sensor configurations and the LH2 flow? That's one question, just kind of to take us through the last 29 seconds of the countdown that haven't been tested yet, and if there's any changes in the process. And then the other question is about the COLAs. How are those accounted for in the countdown? Does Charlie call a hold, or will it be automatically, would the countdown clocks automatically stop, especially if you're already in a termination mode, or would you not pick up the final section of the countdown if there is one of these COLAs in that process? Thanks.
Yeah, no worries. So for the last 29 seconds, no changes were made. Really, in order to kind of maybe get at the base of your question, which was, what did we do to kind of mimic some of the green run activities? That's primarily where we intend to begin the kickstart test. And so that's happening before we get to stable replenish on the LH2 tank. And so we're bringing that much earlier into the flow and before we actually even get the hydrogen tank full. And so that really mimics exactly what we did at a green run. As far as when we go into the last 29 seconds and ALS handover, no changes were made based off that. And so a lot of this is a vestige of not getting all of those objectives bought off during wet dress rehearsal 4, and then really wanting to make sure we have strong process control. Let's see, I'm sorry, can you repeat? Okay, so the COLAs, how do we account for that? Thank you for the reminder. So on that one, it really will depend on when we choose to reset the clock. So say we go in, what happens right now is the GLS integration console. So our ground launch sequencer has a series of times of when those cutouts are. And so if we run into any issues, what we'll do is we'll perform an analysis and say, we are good to launch at X time, and they'll reset to that, and then they avoid the COLA. So it's not completely automated, but we do have folks that have those times up, and it's really when we go about resyncing the clock to a new T0 time.
Thanks. Thank you. Kenneth.
New York Times. So in the last couple of days, we've heard a lot about the hydrogen line bleed kickstart. I was just, and that's to sort of verify your procedures. I was wondering, once that all sorted out, in a normal countdown, when does the engine chill down occur?
Okay, so let me try and get to the core of your question. So when do we maybe I'll repeat it back. So when do we validate our new procedures? Is that the question?
No, assuming everything works the way you want it to this time. So for Artemis 2, when would the chill down actually occur during a normal countdown?
So the kickstart procedure is something that I do think we will do every single flow, and so we'll know that relatively early on. What we are doing this time around that we would not necessarily add into future tests is a pre-press test, and that's just us kind of getting into understanding exactly what the controls are, how everything's behaving, and that's really going to be a risk mitigation to the terminal count. But I do believe we will not continue to do, or we will do the kickstart similar in every single flow.
And what time in the countdown would that occur later?
So right now it's going to occur at approximately 8 a.m. I don't have the T-minus time right on me, but it should occur about 8 a.m. for about an hour.
No, in the future.
It would be at a similar time.
Okay, thanks.
We have some questions on the phone. We have Jim Siegel, NASATech.net.
Oh, thank you for taking my question. If the launch moves to Monday instead of Saturday, when will the launch window open? And I assume that it'll still be a 2-hour launch window. Thank you.
Let's see. So our launch window opens, it's a couple hours later. I don't have that exact information with me handy, so I'll have to get back to you exactly at that time. And so I'll just follow up if you don't mind.
Yeah, absolutely. Jim will get back to you on that one. And then we have Anthony with main engine cutoff on the phone.
Hey there, thanks for taking the call. For Jeremy, if the crack on the core stage foam yesterday was mentioned that that's not an issue for flight, are there any other areas on the core stage where that would be an issue, and how are those monitored?
So we do a series of checks throughout launch countdown and actually in between the last attempt and this one where we go through, we do thorough inspections of the vehicle. Even very minor defects are noted. Throughout launch countdown, we have a team which we call CICE on the console, and they do inspections throughout. So they use high definition cameras, infrared, things along those lines. And so right now we've done a full inspection of the vehicle. We've noted any nonconformances, and they've cleared any of those for flight. Throughout the count, as we see cryo pumping, things like that, we're going to continue to do the same thing. If anything is anomalous, they note it, and then they turn it over to a debris trajectory analysis team to decide whether or not we have any concerns. So they have standards that they use against, and they have models that we run it if it's above those standards. And then just to answer the other question, it was 5:17 p.m. is the launch time, and I believe it is a 2-hour window as well.
5:12, actually. 5:12 on the, yep. Nope, it's okay. It's 2:17 Saturday. So 5:12 on Monday, no problem, with that 90-minute window to answer Jim's question from before. And we had a question in the room here. Yep.
Aaron Cooper with CNN. Knowing everything you know, can you kind of bottom line it for us? How confident are you that this is going to fly on Saturday? How confident are you it's going to fly before the end of the Tuesday windows?
Yeah, so this is a test flight, right? And so while I feel very good about our procedures, when you look the team in the eye, they're ready. We can't control the weather. And so on any given day, there is risk that we'll be able to get off. I think what I kind of am looking at is our team is ready. They are getting better with every attempt and actually performed superbly during launch countdown number 1. So in my mind, I think if the conditions with weather and the hardware align, we'll absolutely go. And we have the right team at kind of the right time. So in those statistics, right, those probabilities go way up if we get 2 attempts off before the end of this window.
And I believe there was another one in the room. Was there another hand in the room? No? Oh, over here.
Hi, I'm Brandy Campbell with Fox Weather. With the weather being favorable at 60%, how often have you guys had a successful launch at that, rate? And with that being the rate, do you foresee us maybe waiting a while for like a good time to take off, or is there a chance we could take off, at the beginning of the window?
Those are excellent questions. I don't have the exact stats that you're searching for. I can get back to you with that. I can tell you, though, that on any given day, there's about a 1 in 3 chance that we will scrub for any reason. And out of those chances of us scrubbing, there's a 50% chance that it's due to weather. So hopefully that's some stat you can take back. Could you remind me of the second part of your question?
Yes, I was asking, is there a chance that we might have to wait a while for there to be a good opportunity for us to launch throughout that weather, being that it's a 60% chance favorable?
It's entirely possible, and that's why I trended the forecast as such, I did today, making it worse at the beginning of the window and a little bit more favorable at the end. It really all depends on that sea breeze and whether it moves inland as fast as we are expecting. If we are looking at the balloon data in the morning and that easterly flow is not nearly as established as we were hoping to see, we could run into a situation where we're red a little bit longer than we expect to be. But overall, that sea breeze does tend to win out with easterly flow, regardless of truly how strong it is.
Okay, we don't have any other questions on the phone. If we're done here in the room, then I think we can wrap up today's news conference. Again, thank you, Jeremy, Melody, and everyone who asked questions. For more information on Artemis 1, we're going to pull up some resources here on the screen. You can take a look at this website. Also follow us on the social media channels you see there. Coverage of us tanking our moon rocket will begin at 5:45 a.m. Eastern Time tomorrow on NASA TV. And then our live launch coverage will begin at 12:15 p.m. For our Spanish viewers, our Spanish launch broadcast will begin at 1 p.m. We hope you can join us. Thanks so much.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Being an educator today is not easy. We here at Heights Elementary School are not here simply to educate our students in the academic realm. It's so important for our students to be lifelong learners, and we have to think about ways that we motivate them to do so.
There are so many distractions that we have to compete with.
iPads, Xbox, video games,
Internet.
Far too many channels of cable television.
What we need is something that kids will be highly motivated about, something to keep them physically fit as well as making nutritionally sound choices.
What we needed was a new tool to help these kids think about diet and exercise in order to make the healthy choices they need to.
I knew what that tool was. It was something that inspired me as a kid and continues to inspire me today. The space program.
The importance of an astronaut's physical exercise and proper diet cannot be understated, not just for the fitness of the astronaut, but also to ensure that they stay mentally focused and productive during their stay on the International Space Station and for future missions, whether it be to asteroids, the moon, or Mars.
In response to the rising childhood obesity rate, NASA has developed a series of activities based on astronaut training, and we call that Train Like an Astronaut.
Examples of the Train Like an Astronaut activities include things that we do exactly as we do on the ISS: cycling, resistance training, and cardiovascular. And then onto dexterity, putting puzzles together, making healthy food choices, and working as a team. All activities as they truly do on the ISS.
Train Like an Astronaut activities are flexible enough to be used in conjunction with other programs like NFL Play 60. What makes this program unique is that we're using the human challenges of spaceflight to inspire as well as motivate our children to make healthy choices throughout their life.
We're currently in 24 countries with over 24,000 participants and growing every year.
This has expanded to such an incredible opportunity for both myself and for educators around the world to make such an impact on the lives of children, both with fitness as well as nutrition.
It was excitement for the whole thing that the students, they weren't just doing exercises anymore. They were training like an astronaut.
The true success of this program is the educators. An example of a teacher that has worked and motivated his children is an outstanding educator by the name of Tim Vigorito. This gentleman excited them and inspired them in ways that we never could do it. And with that, he's helping us grow the 21st century leadership that we so desperately need.
Mr. Vigorito is extremely passionate about the Train Like an Astronaut program.
I think he himself would like to be an astronaut.
He comes to life when he's teaching the kids and talking about the program. The kids feel that enthusiasm.
We're just so fortunate to have him. Oh, it's truly the case.
They say your astronaut training doesn't begin when NASA hires you.
Cool.
It begins when you're young, by learning about space and the world around us, and by making healthy choices in life. Today, I'd like to recognize an outstanding physical education teacher, Tim Vigorito, for being a champion for the Train Like an Astronaut program and influencing thousands of students to date.
Wow.
It is educators like you that truly make a difference in this world and who will inspire the next generation to propel humankind on future missions to Mars and beyond.
This is too much. For me, it's become a way of life. And I'm just so thankful to everyone for what it's done for me. I just want to share that with my students. Maybe it'll inspire them to reach a little deeper or to go a little further or maybe to try a little harder, whatever it is in life.
The International Space Station is the most fantastic vehicle ever built.
It's a one-of-a-kind laboratory orbiting about 250 miles above the Earth.
And we perform experiments on the International Space Station.
We can do science, we can do experiments, we can learn how to do things out of this world. And the result will help benefit the people on the ground.
The space station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
The weightless environment will give us insights into things like diabetes and maybe even cancer.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
If we wouldn't have conducted experiments on the ISS, we wouldn't have known that you could use cold atmospheric plasma in such broad application areas we're now exploring.
One of the most promising results has been gained by studying a protein associated with Duchenne muscular dystrophy.
We may be able to slow the disease by half, potentially doubling the lifespan of many of these DMD patients.
We provided eyes-served imagery for many natural disasters, including floods and fires, for deforestations, for volcanic eruptions, and for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
I think it's made people much more aware of the issues of water quality. That's a very powerful thing.
Having the HICO on the International Space Station has been the ideal test bed for our research.
We can monitor these water bodies from space, and if we can reduce exposures both to humans and even animals, then we've achieved our goal.
And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The space station has done so many things for life on planet Earth. It shows us what human beings can do working together. It shows the science that we can discover.
Over 2,000 experiments have flown on board ISS. 170 countries around the world have participated in some fashion, either in the ISS itself or in one of the experiments. Our rate of research is actually increasing. We're doing more today on board the space station for research than we have ever done before, and that's only going to continue in the future.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
Headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled, and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of times we'll find out after the fact that there's a problem with cyanobacteria in the water because the blooms already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HICO, which stands for the Hyperspectral Imager for the Coastal Ocean. HICO consists of two instruments. One is a camera,
And the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HICO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HICO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HICO on NASA's International Space Station. As HICO acquired a scene, it was transferred to the Naval Research Laboratory. And then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information. But the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
As farmers and winemakers, we work very hard to grow the best quality fruit possible to make the best wines possible. The real polished part of winemaking is letting that wine age gracefully so those flavors can be preserved and brought to your home and to enjoy in the glass. The greatest issues we face as winemakers is that our optimal storage conditions for our wines are also optimal growth conditions for mold and bacteria.
Mold is really bad in a barrel room or in a cellar because it has an odor to it. And the wines are a living, breathing thing. And actually, they pick up the characters of where they're living.
The wines can absorb that aroma, and it's just not a healthy environment to work in. My father and I built this barrel room underground. The challenge is we've got some stagnant air which can cause mold growth. Who knew that our solution would be not underground, but up in the sky?
In order to carry astronauts to Mars for deep space exploration, you have to be able to grow your food storage. You don't have enough space and capacity to carry them with you. So NASA began experimenting with growing crops in space. What they found is that in the growing chambers on the International Space Station, the crops they were growing were emitting a naturally occurring hormone called ethylene. It's a gas, and ethylene is the reason that fruits and vegetables ripen.
But the problem was in space, we're going to have a very confined environment, so the ethylene concentration can build up, especially in a plant growth chamber. It basically destroys the plant. And so there was a need to grow plants in space, and we were good at growing plants here at the University of Wisconsin. And so NASA came to us and said, we've got a problem. I think you've got a solution. Can you help us?
Through the University of Wisconsin Advanced Astroculture Program, they developed an ethylene removal system that was successfully tested on a number of missions on the International Space Station. So the ethylene removal system that was developed draws air through a reaction chamber. The air is passed across a catalyst bed, and that catalyst has the effect of removing anything organic from the air. That includes mycotoxins, bacteria, viruses, and even mold.
It showed us that with the right technology, we can overcome the challenges of growing plants in space and enable future space explorers to grow their own food as they continue to explore the solar system.
The International Space Station program not only supports the technology that allowed us to get rid of ethylene in the space station astroculture program, but it also provides a great variety of technologies to exist that otherwise wouldn't have been possible.
Realizing that this technology could have tremendous benefits here on Earth, we developed the Aeroside air purification systems. Initially used in the perishables world for prolonging the shelf life of fruits and vegetables, not long after that, we realized because of the effects the technology has on mold, that the wine industry was a perfect complement for the technology.
This technology has been a real boon to us. It helps me sleep better at night.
But as you can see around the cellar, there's not a lot of mold.
Within 24 hours, the amount of airborne mold spores were dramatically reduced.
Within 2 weeks, about 99.9% of the mold had vanished on the walls.
It solves problems before they occur.
The room smelled fresher. It actually enhances your storage conditions for you to even make better wine.
It's really amazing when you think about all the innovations that are going on up in space, how they can come into a place as unexpected as a winery, which translates into benefits on your dinner table.
Surveyor is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was really a fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it iServe, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from iServe.
And we moved to like 1,000 images per day.
We provided iServe imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world. So this is something that was not really there before.
iServe is an example of, in essence, making the International Space Station even more international and connecting space to village to better understand and protect our home planet.
From the solar winds to the mystical auroras, science is a way of knowing, a way to help us understand the world around us. But how do we learn about the things we see, and how do we make sense of the things we don't understand? Find out next on Real World. As humans, we're all really curious about the world around us. Science is a way of knowing, but what does science really look like? Let's drop in on some NASA researchers who are currently working from home. Dr. Nicolene Weil studies the sun and solar winds by analyzing data from spacecraft, like NASA's Solar Dynamics Observatory. Dr. Marilia Samara studies charged particles in space by sending rockets into the auroras. And Amber Versteinen is an undergraduate student majoring in atmospheric science. Amber's internship at NASA helped put her on the path to a career in science. Dr. Weil, can you help us learn more about the nature of science?
Science is about understanding the natural world around us. Science is about finding new information, which inherently comes with being wrong a lot of the time. By definition, you're exploring space and questions that nobody has really thought through before.
Dr. Samara, how do these questions drive the study of science?
We'll ask questions. We try and figure out what experiment might help us answer those questions. We go for it. Usually we don't figure out enough. We try again. We had no idea how the aurora was created, but people would notice that when they had a compass and there was aurora going on, funny things would happen. So they knew it had something to do with the magnetic field.
Scientists use different methods and tools to gather a variety of mathematical data. Data may include images, numbers, patterns, shapes, and calculations that help model and describe the world around us.
So think of images just with like a camera. That's a remote data set. You can do it in optical light, the light that we can see with our eye, just like with a regular camera. But we can also look at the sun in other wavelengths, other types of light, like X-ray light, ultraviolet light, infrared light. And so those are give you other types of information about the sun. The other type of information that we can get is called in situ, and that means measuring directly where you are.
In the case of aurora, we're trying to launch and go over the aurora in what we call the apogee, which is the highest point from the ground, and make measurements there. By concentrating on the apogee, is we effectively get a snapshot of how the environment, that space plasma environment, looks at that particular time, at that particular altitude. It's surprising how much science is in just a couple of minutes of these measurements.
When we look at data for a long enough period of time, we can understand patterns in those data and really make sure we're not just answering one little question about the sun, but that we're really pulling all of the information together and making sure the big picture still makes sense of how we think the sun works. When good science is being done, it leaves room for us to change our mind, to realize we were wrong about how something was working as we get new information, and we have to refine our ideas about how the natural world is working.
Scientists do their best to understand observations with the knowledge and tools they have, but sometimes scientific explanations change.
So I think of science as basically a puzzle. We have tiny pieces of the big puzzle. Every time we have a new piece that actually connects, our image changes.
We do our best to describe what we see and what we're observing, and then we figure out which parts still aren't making sense. Sometimes a model will make sense and explain all of the observations that we have today, and then tomorrow the sun will do something totally different and we'll have new observations. And it's not even necessarily that the model was wrong, it's just that the model was incomplete.
It's important for all of us to understand the nature of science because we can all be scientists, asking questions and gathering data. Amber, you've had a chance to collect data during your internship at NASA. What were you studying?
While I was in high school, my first project was studying ozone and how it affected plants by working on an ozone garden that was at the Virginia Living Museum. An ozone garden is a garden that consists of like different types of plants, some that react to ozone and some that don't. So some of the tools we used was a meter stick to measure the heights of the plants. We used a rain gauge to measure how much rain all of the plants were getting. We used a thermometer to measure the air temperature that the plants were growing in, and we used a psychrometer to measure the relative humidity of the garden each day. The ozone garden research was really important because it shows how different plants grow more efficiently in different climates and how ozone has such a big effect on the plant growth. This is really important to understand with our changing climate.
A new fact is really like a new piece in a science puzzle. As more pieces are added, the big picture becomes clearer and clearer. But it's important not to try to force any pieces that don't fit.
It's important when we do science to do our best to overcome our biases. Everybody has biases. It's important to be ready to be proved wrong.
Science is a human endeavor, and our understanding of science is constantly changing. Men and women from all cultures and backgrounds choose careers as scientists and work in teams to answer the questions we have about the world around us. So, how can you get involved?
So don't just sit there. Ask a question. Make an observation. Use all the tools you have to collect evidence. Even do a citizen science project. You could even do an internship, maybe even at NASA.
So what are you waiting for? Science is an amazing way to use math to help uncover grand mysteries in the natural and material world. Special thanks to Dr. Nicolene Weil and Dr. Marilia Samra for helping us understand more about the nature of science. And thank you, Amber, for helping us see ourselves as scientists. I'm Sarah, and see you next time on Real World.
NASA Marshall Space Flight Center is Science Central for the International Space Station. Our teams help astronauts conduct groundbreaking research in microgravity. We have supported more than 3,400 investigations from around the globe. Our operators work with researchers, commercial companies, and even students to expand scientific discoveries on the orbiting laboratory. Now let's hear how each flight controller position is critical towards making science happen in space.
Welcome to the Payload Operations Integration Center. As a Payload Operations Director, I manage the day-to-day operations of science experiments performed on board the International Space Station.
The science experiments on the International Space Station range from studying human physiology to dark matter and even growing plants in space. As a Payload Rack Officer, our job is to monitor and ensure the safe operational use of these experiments.
It's very important that tools and parts are safely organized on the International Space Station. Every day, stowage engineers track the location of these items so astronauts can easily find them to conduct science experiments.
The PACOM team talks directly with the ISS astronauts, guiding them through science experiments and technology demonstrations. The crew are our system, and we advocate for them from the ground.
Analyzing, integrating, and communicating. These are the responsibilities of an operations controller. We ensure that the astronauts have the resources they need to complete their science experiments safely.
Sometimes even the best plans need to change. Timeline change officers work with NASA centers and scientists from around the world, developing the best plans for each science experiment.
It is important that science data is transmitted down to Earth. As a data management controller, I help to ensure that data from space station is sent to scientists around the world.
The Marshall Ground Control Team ensures that all ground equipment is fully operational, such as computers, servers, hardware, and software. We also make sure that all data is successfully sent to and received from the satellites.
Thank you for visiting. We hope you've enjoyed this behind-the-scenes look at how Marshall enables scientific discovery.
When you consider a busy street in a large urban city, what thoughts come to mind? Perhaps honking cabs, cars, or large crowds of people all trying to get to their destinations? Although that picture of a city may seem like a chaotic mess, the reality is that generally, traffic and people move in a relatively orderly fashion. For the most part, cars stop at traffic lights, pedestrians cross when safe to do so, and everything works as it should, even if it's crowded. This system of traffic signals and rules of the road has been in place for many decades, so this type of movement is accepted as the norm for how we get around in a city. But what was city travel like before the invention of traffic signals? There are many stories of pedestrians dodging oncoming cars, horse-drawn carriages and fast-moving cars fighting for space, and just general mayhem ruling the day due to a lack of a well-thought-out plan. There were already rudimentary manually operated signals in operation, but with only a stop-and-go signal, they were not very effective. This left drivers little time to react when the command changed. It was clear when automobiles became more prevalent in the urban environment that a viable solution was needed to lessen the unpredictable nature of traveling in a city. That solution was found in November of 1923, when an inventor named Garrett Morgan came up with the answer. After witnessing an especially bad accident one day, Morgan designed and patented a 3-position traffic signal, which used an automated signal with an interim warning position, the predecessor of today's yellow caution light. With this invention, cities around the world began to adopt this new technology, making the streets safer for cars and pedestrians alike. That fundamental change for city driving came about 100 years ago. Ironically, today, there is a situation in our modern world that is in need of a similar solution, but it will take more than adding a yellow light to solve this new problem. NASA, the FAA, and more than 100 industry partners have tackled the proliferation of unmanned aircraft and the need to regulate and manage these small drones. Just in the past few years, more than an estimated 700,000 unmanned aircraft systems, or UAS, have been purchased and are flying around our skies. With the push for these unmanned aircraft to be used in our daily lives for tasks such as delivering goods to our doorsteps, monitoring traffic on highways, recreational uses, and for medical needs, to name just a few, imagine what our world would look like in a few years if a dependable system of control was not put into place. Many have questions how such a dramatic change to the airspace will affect our lives and safety, and with that, NASA has set out to create a research platform that will help manage large numbers of drones flying at low altitude along with other airspace users. Known as UAS Traffic Management, or UTM, the goal is to create a system that can integrate drones safely and efficiently into air traffic that are already flying in low-altitude airspace. With UTM, package delivery and recreational flights won't interfere with helicopters, airplanes, nearby airports, or even safety drones being flown by first responders. On this episode of NASA X, we will examine this award-winning UTM technology and see how it works, and better comprehend this innovative system. We will also take a look at the dedicated NASA team at various field centers and its government and industry partners to understand the work accomplished developing and testing new software in real-world research. And we will see the system in action and find out when these new innovations will come online. Not too many years after the first flight at Kitty Hawk, North Carolina, NASA's predecessor agency, NACA, began developing technology and systems that have revolutionized the way we fly. NASA took over this workload from NACA in 1958 and has continued to pave a path forward for the aeronautics community ever since. As the premier science and technology agency in the federal government, it makes sense that NASA was once again tasked with understanding and developing a new system to make sure the drone technology would be world-class and safe from day one.
Well, there's a lot of reasons NASA is doing this work, right? So we can have a nice working relationship with industry as well as with the government side, the FAA, the DoD, DHS, DOI, that whole alphabet soup of folks that are interested in this space as well. We can bridge that gap between industry, the public, and them, as well as bring our experience in the airspace and in aeronautics in general to solve the problem, right? So building that coalition, coming up with unique solutions, testing them in the field, making sure that we have all the parties involved. That's really the sweet spot where NASA sits for this kind of thing.
NASA teams have been looking at unmanned aircraft technologies for quite a while, trying to better understand how large, medium, and small drones will begin to be integrated into our national airspace. Early conversations with the Department of Defense just needed NASA to help transition unmanned aircraft into the U.S. airspace. But those needs began to transform to a bigger picture almost immediately.
When we got involved in this, it was a pretty simple problem that we were trying to solve. DoD was bringing unmanned aircraft back from theater. They needed to move them from one base to another. And so the question was, how do you get these very high-performance unmanned aircraft up into Class A airspace? So take off from restricted airspace and move through Class E airspace up into Class A. And that, that's real geeky sounding and all, but for the FAA people, this is really important. So that's what we thought the problem was. After we had started working in this just for a couple of years, along came this package delivery. So a whole new mission and a whole new set of actors came out. So it took on a whole new meaning. NASA then got very interested in how you manage the traffic as well as what the characteristics of the vehicle should be. So when we first started, it was all vehicle centric. But then as we got real interested in UTM or UAS traffic management, took on a new meaning of how do you manage all of these vehicles around? And it has just blossomed for that into hundreds or thousands of use cases. And everybody that could possibly think about delivering some service or some product to a household or between businesses now has an interest in the work that we've been doing.
With the knowledge of building a completely new system that would fundamentally change how vehicles move in our airspace, the team needed to carefully understand the major issues. So they took a step-by-step approach to make sure they were moving in the right direction. They first had to lay out the goals, which included, but were not limited to, allowing diverse, small UAS mix and airspace use. For example, package delivery, safely enabling scalability for the future, and establishing a highly efficient, predictable, safe, and affordable airspace operations system, all by developing and validating integration requirements and providing prototype software UTM systems for the FAA to further test.
So NASA developed this concept called Unmanned Aircraft System Traffic Management because we are expecting millions of drones and their operations in a day, which is magnitude order different than what happens with current aviation, where there are 50,000 aircraft, and at a time there are about 6,000 at peak in sky. So the question is, how do we manage these millions of drones without burdening the current air traffic control system? Now, there are fundamental differences in the way the manned aviation works and the drone operations will work. First of all, there is no pilot. Second, that these drones are small. Third, we can actually take advantage of digitization and connectivity across these drones by exchanging information to each other. So the idea of UTM is taking advantage of modern technology, making sure we don't overload the current air traffic control system. Now, one of the big parts of UTM is this managed by exception paradigm. In today's operations, air traffic controller is the only one that has all the information on the radar display. With UTM, we can connect all the information, and that information can be shared across all the operators in the sky. That allows us to basically say that Just tell me what not to do, and I will figure out a path that will avoid other vehicles in the sky.
As PK mentioned, the system is a bit different than the air traffic control system used by the Federal Aviation Administration for today's commercial airplanes. UTM is based on digital sharing of each user's planned flight details. Each user will have the same situational awareness of airspace, unlike what happens in today's air traffic control.
Well, with the projected number of new drones coming in the commercial markets for a very large number of drones and operations, it's obvious that the current air traffic management paradigm, a human air traffic controller communicating with one or a handful of vehicles, will not scale up to the number of operations of commercial drones that people are thinking about. And so a new way of controlling this traffic had to be established or thought up. And so NASA came up with the idea and vetted it through the FAA and industry to have this automated system that really did not rely on human air traffic controller interaction. And the key to this is that industry would be providing these services. And this would foster competition and economic growth and such for the system. And so this whole development of this traffic management system, not manually controlled by the air traffic controllers, but by automated systems provided by third-party industry commercial providers, really is a major change in the way air traffic management will be done in this country, and necessary to satisfy the vast number of new entrants in this growing drone market.
You think about the different ways that the system will impact people's lives. One simple one is ordering things online, right? In the future, you may be able to order something. It could be delivered to your house by drone in minutes to hours, as opposed to, days. That's one use case, right? So people can say, oh, wow, that would be neat. Also, you can think about public safety, right? For example, fire departments. One thing they would like to do is to send a drone out before the truck can get there, right? It's possible for the drone to get to a site faster than a truck can, and they can survey the scene before their folks actually arrive. So again, that's a public safety feature that people can usually feel good that our system, a system like we've designed that may be implemented in the future, could help support. So let's imagine both of those things happening at the same time. Someone trying to deliver a hot dog to your house, and then actually a fire happening and the fire department wanting to get through. The system enables those kind of interactions, and it keeps the airspace safe. It keeps things from falling out of the sky. It keeps all the stuff working properly.
To begin problem solving, the team created 4 individual technical capability levels, or TCLs. TCLs are a risk-based development and test approach. TCL-1 served as the starting point of the platform, with drones flying simultaneously at 6 test sites, while each test site operated on their own schedule. TCL-1 focused on areas of remote population, low traffic density, rural applications, and work on notification-based operations. Researchers conducted field tests addressing how drones can be used in agriculture, firefighting, and infrastructure monitoring, and working to incorporate different technologies to help with flying the drones safely, such as scheduling and geofencing, which restricts the flight to an assigned area. After completing these valuable tests, the team then moved into the second stage of the testing, TCL-2. For TCL-2, NASA performed a 5-day flight test at the Nevada test site, with additional flights taking place for the national campaign at an additional 6 FAA UAS test sites. This testing was focused on monitoring drones that are flown in sparsely populated areas where an operator can't actually see the drones they're flying, known as beyond line of sight operations. Researchers tested technologies for on-the-fly flight adjustments in controlled airspace and technology to clear airspace for search and rescue missions or for loss of communications with a small aircraft. As the UTM team monitored these flights, researchers also introduced simulated aircraft into the same airspace occupied by the drones to add more complexity in the system. The drones flew profiles that simulated real-world uses, such as package deliveries, farmland surveys, infrastructure inspections, search and rescue missions, and video surveillance operations. This work was proven successful, and the team quickly moved on to the next phase, TCL-3. TCL-3 was flown at the 6 FAA-designated test sites and focused on creating and testing technologies that will help keep drones safely distanced and flying in their designated volumes.
The UTM project also included the development of onboard technologies to help mitigate the risk from drones, both for those in the air and on the ground. These technologies are designed to help recognize and address potential problems while in flight and without human intervention. One of these technologies allows a drone equipped with special sensors and software to autonomously sense and avoid other aircraft.
This capability level also tested vehicle-to-vehicle communications in areas with moderate UAS traffic density. Testing also included UAS ground control interfacing to locally manage operations, communication, navigation, surveillance, human factors, data exchange, and network solutions. Drones were also flown beyond visual line of sight and in close proximity in altitude and distance. The focused technology flight tests were conducted at Langley and Ames research centers and complemented the flight testing conducted at the designated FAA test sites. Both provided valuable information of the flight performance of the drones necessary to work within the UTM system. Since UTM is a new way to manage air traffic, human factor data collection in real-world conditions is critical to understanding the human-system interactions.
We're really breaking new ground on the way human operators interact with complex systems. And so being here helps us get data on exactly their experience with this system. So for example, we are kind of monitoring the communication patterns that they use. So UTM as a system is exchanging lots and lots of data, and that data can be presented to those operators in a variety of ways. And they also have other ways that are not UTM to communicate with each other. They can communicate with each other over their radios. They can communicate each other through like texting applications, right? So we're kind of measuring all of those communication patterns to see what things are they talking about through UTM means and what things are they talking about with outside of UTM means to really give us a sense for how well UTM as the system is supporting operators in conducting their operations.
Finally, TCL-4 demonstrated how the UTM system can integrate drones into urban areas. Corpus Christi, Texas, and Reno, Nevada were chosen as the test sites, offering the right mix of challenges to prove that UTM could work anywhere. The cities have large populations, many obstacles to avoid, windy weather conditions, reduced lines of sight, and fewer safe landing locations. TCL-4 addressed these challenges using UTM systems and technologies on board the drones and on the ground. These include incorporating more localized weather predictions into flight planning, using cell phone networks to enhance drone traffic communications, and relying on cameras, radar, and alternate ways of seeing during flight to ensure drones can maneuver around buildings and land safely, all while communicating with other drones and users of the UTM system.
Over the kind of the progression of this project, where we are now is the most complex piece of it, right? So now we are testing in urban environments, in higher density operations, looking at kind of contingency or off-nominal situations. So that list of three things, urban environments, higher densities, off-nominal situations, those are all extremely complicated things to tackle. And so for us to be here tackling those things is the only way we could learn some of the things that are associated with those things. That would be all very difficult to learn in a laboratory setting. There are so many things that are really an opportunity that come from the geographic locations in which we are testing that give us these types of this data, everything that we learn from being here.
Although all this research took place here in the U.S., this new structure will be the framework used around the world.
UTM idea, concept, architecture is out there, and it's been endorsed by ICAO, the International Civil Aviation Organization. And if you look in Europe and in Asia, countries that are starting up their version of UTM, they're starting with this architecture that NASA developed. And so it's really out there. And we're participating in international standards groups to really kind of consolidate what the concept is and harmonize internationally.
The influence of UTM on future projects, I think, was something we're pretty proud of, right? The concept and the way of managing the airspace is really new. And people are seeing application of that to, for example, UAM and air taxis, potentially for high E operations over 60,000 feet, space traffic management. All of these things can leverage what we've learned in UTM because it's about providing services to classes of operations where services aren't provided now and probably won't be provided. Right, so finding a solution to that really has benefited future work as well at NASA.
It's clear to see that a tremendous amount of planning, research, flying, design, and hard work went into this project, and that the UTM framework is here to stay.
I think we're really getting into a whole new era of aviation, right? Where we got completely new operations that weren't there before. We are envisioning a few years from now, maybe 10 years from now, a world where we'll be traveling through cities in small electric aircraft, for example, and we'll have our drones delivering medicine or delivering food or things like that. All this is really only going to be able if we set like a foundation where we can use our great new automation capabilities, networking capabilities, really making use of digital ways to coordinate all these different operations and all this air traffic in a way that just wasn't possible before. But the only way that we can actually do this is by shifting the paradigm entirely from this very human-centered approach that we've been taking over so many years to safely manage all this traffic that was existing for these new operations, to take an approach that is a lot more built around safe frameworks in which the different technologies can interact with each other and where they actually are going to be able to provide the first level of safety layers and the core components of organizing all this traffic.
UTM is enabling airspace operations and providing access to users that was never possible before. It's opened up skies in a way that we can now enable different types of operations in the airspace, and we have a way to manage the traffic because of UTM, which gives tremendous societal benefit of reaching places, cargo as well as people, that was not possible before.
Low-altitude airspace is leading a revolution in flight, and a multi-billion-dollar industry is emerging as a result. At no time in history has aviation been poised to enter the lives of so many people. From package delivery to first responders to safety inspections to video documentation, every person stands to benefit in ways we have only begun to imagine.
We're really at a once-in-a-lifetime opportunity to be part of aviation. We see new aircraft like we've never seen before. We have new types of software systems, scalable and cloud-based. We have new companies that are entering the space that we haven't traditionally seen in aviation so far. And we have really great collaboration amongst industry to work together, as well as collaboration with the FAA and aviation authorities to go ahead and make that happen. And that really sets us up for the next 100 years of aviation in a way that we haven't seen before.
The research and development completed on the UTM project has come to a close, but that doesn't mean that the final chapter of this technology has been written. NASA and its partners are planning future research and testing to mature these systems to the point that one day soon, flying drones in our neighborhood will be as common as seeing yellow caution signals on traffic lights. With the success of NASA's UTM project, that day is much closer than you may think.
Scan the beginning, and we see that communicating to, from, and in space was all NASA all the time. Our satellites, our infrastructure, our people. Today, some 6 decades later, filling the vacuum of space communications is competition. Commercial industry has come a long way in the past 40 years, and now may reliably deliver most of those same satellite services to space-based users in the near-Earth environment that were once the exclusive domain of NASA. So NASA Space Communications and Navigation, SCAN, will be investigating viability of the commercial space-based networks to meet the needs of NASA missions flying around Earth. Once demonstrated, NASA intends to move away from government-owned and operated systems and procure commercial comms services. NASA cares about the health of the U.S. satellite industry and will work with everyone to promote industry growth, innovation, and interoperability. By 2030, NASA SCAN expects to migrate from the current paradigm of operating and maintaining government communications systems to a new one where NASA is just one of many commercial customers in an interoperable near-Earth space, exclusively shopping the commercial marketplace for the best and most cost-effective services to support our closer-to-home NASA missions.
Liftoff of the Falcon 9 and Crew.
NASA expects the space-based market to grow tremendously over the next few decades. Like the successful Commercial Crew program, NASA SCAN will trust its more routine, time-tested tasks to industry innovators and collaborators who'll partner to expand satellite industry norms and standards and embrace interoperability. They'll augment existing processes with autonomous operations and navigation services, critical for meeting user needs in a highly congested and dynamic environment. Scientists and mission engineers will seamlessly roam space-based relay and direct-to-Earth communications networks, enabling them to immediately access the freshest data, download the most recent revealing imagery, and at a moment's notice, nimbly turn satellites and telescopes to cover breaking science, like a volcano erupting unexpectedly or a supernova appearing suddenly in the night sky, all in a user-friendly experience as simple and seamless in space as a call with your smartphone on Earth. And the money NASA SCAN saves in near-Earth orbit will help fund game-changing technologies elsewhere, such as multi-GNSS receivers that work at the moon, multilingual space receivers that can be reconfigured on the fly to communicate and negotiate with any provider for access to their networks, and systems like optical and quantum, literally the waves of the future in NASA deep space communications and navigation. Scan the future, and we see greater efficiency and sharpened focus for NASA, and for our nation and its workforce, a more competitive, innovative, and interoperable space communications industry. NASA Space Communications and Navigation. SCAN. Exploration enabled.
Humanity has always been interested in exploration. If we really want to go to the moon, we have got to figure out a way to keep our propellants cold long enough. My name is Monica Guzik, and I have the coolest job at NASA because I work with cryogenics. Cryogenics is the study of things at very low temperatures. We've got electrical connectors we can plug into. So we want to store things like oxygen or hydrogen, but if you store them as a gas, the only way to get a whole bunch of molecules in there is to raise the pressure really high. So instead, if we make them really, really cold, they turn into a liquid, so they're way more efficient to store. So this is gonna be a liquid oxygen test. I always knew I wanted to be an engineer since I was a little girl. My dad was an engineer, and I just thought engineering was so cool. We were gonna put insulation over this. Ended up getting a summer internship here at NASA Glenn Research Center in Cleveland, and just really sort of fell in love with NASA. Cleveland is the rock and roll capital of the world. I really enjoy rock and roll music, so I try to go to a lot of concerts. When we improve cryogenic technologies for space applications, it always has a trickle-down effect to the Earth. Now we're rolling into the Artemis generation, and we're still doing that.
1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind: the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Hi, I'm Serena Anand-Chancellor. I'm a NASA astronaut, and this is Ask NASA, and I'm ready for your questions. All right, so first question, what is Artemis, or what is the Artemis program? So the Artemis program is our lunar exploration program. We will get to the South Pole of the moon by 2024, landing the first American woman and the next man. Why are we doing this? Well, in order for us to head towards Mars, we need a special place where we can practice, essentially develop robust engineering technologies, figure out how well the human does with long-duration spaceflight, learn how to build habitats, and we do all of this on the moon. Essentially, we practice. It's an engineering battleground, so we can go to Mars. What do you think it'll be like to go on an Artemis flight? Well, let me tell you, this would actually be really cool to go on an Artemis flight because we'd be heading to the moon. Now, what vehicle will we be traveling in? Well, it's actually the Orion vehicle right here. And some of you may recognize this. This is similar to the old Apollo capsules, but it is bigger, it is better. I've actually climbed inside the mock-ups, seen the systems, very modern systems. This is what will be taking us back to the moon. It's going to have the first American woman on the moon.
Serena, did you always want to be an astronaut?
I did, probably since I was 8 years old. My dad finally asked me one day, do you want to be an astronaut? And I said, yes.
What one personal item did you take to space?
Oh, I took multiple personal items. It wasn't just one. Funny enough, I took a back scratcher because you need a back scratcher wherever you go.
What food would you take to the moon?
Oh, easy. Cheeseburger, French fries, every time.
Yum. If you were to dance off with an alien, what song would you pick?
That's easy. It'd be Michael Jackson's Billie Jean. We played this song on the launch pad.
What do you miss the most about Earth when you're in space?
I missed feeling the Earth. So I miss the wind. I miss the rain. I miss the smell of the Earth, the smell of the grass. These are things you just can't imitate on station.
Is it scary being in space?
It's not scary being in space. I mean, it's your home, and it's the size of a 5-bedroom house. It's absolutely huge, and your friends are up there with you. So what's better than that?
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
We are at Kennedy Space Center. Every piece of hardware necessary to return to the moon is now here.
They are being assembled, stacked, fueled, and primed for flight.
The next time these engines fire up, we'll be on the launch pad to send an uncrewed Orion spacecraft around the moon on a flight test for the Artemis 1 mission.
It's been a journey of 1,000 miles from factory floors all across this country and around the world to here. And now the stage has been set.
We are seeing Artemis take her place.
The framework to support the enormity of this moment can't be measured in renovations and rehearsals alone.
But in the testing of a metal found much deeper.
With each segment built upon the one before it, the volume of anticipation can be seen rising.
For in addition to certifying what a host of testing has already previewed,
and liftoff. The dawn of Orion and a new era of American space exploration.
Artemis will demonstrate a new path to the moon for this generation.
Artemis 1.
An uncrewed test flight will be a final proving of every system
In every component.
in the harshness of space.
A mission that, when successful, will open the door for the moonwalkers and lunar experiments
That so many have hoped and dreamed about.
We are going.
Three, 2, 1, 0. Ignition, liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program. And there are companies all across our country that have a part in it. So there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the service module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway,
We're going to the moon to explore, and we're going to the moon for scientific discovery.
Our destiny is always to go and see what's further and what's next.
The moon is a stepping stone, and the moon is a place we need to learn how to live so that we can continue to go beyond.
We are focused. We are focused on all that lies before us. Only together will we bring to life this global ambition of returning to the moon. And while our work is far from finished, we've never been closer to seeing a new generation step beyond our home planet. We are building on the achievements of those who came before. The giants who conquered gravity and raised a banner in the heavens, they beckon us to go farther, to the moon and on to Mars, to seek a deeper understanding of our universe and bring all that we learn home. 2020 was a year of unpredictable hardships, and yet, step by step, we resolved to press forward toward this grand vision. The daily efforts of thousands of suppliers from all across this country and around the world fed into stunning milestones and laid the groundwork for history.
Launch team, go.
Artemis has been woven into our culture. It has fostered collaboration across the aisles and across the ponds. It has grown beyond plans and preparations to include hardware and software. And now, it has a heartbeat. You can feel the momentum. It is undeniable. We are going. And together, we will see Artemis light the way.
Our mission to the moon is no longer some far-fetched dream. This is reality. We are going.
This is the next step in evolution.
They're not just PowerPoint slides. They're actually metals being bent, shaped, formed to build the things that we're going to use.
This is real. This is going to happen. We're going.
We are going to the moon to learn how to live on other planets for the benefit of all.
Let's go.
We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of peace for all humankind.
We soar in the skies of our home planet. We maintain a human presence just outside of gravity, and we touch points all across the solar system and beyond. We're going back to the moon, and this is why.
The moon is a treasure trove of science.
It holds opportunities for us to make discoveries about our home planet, about our sun,
and about our solar system.
The wealth of knowledge to be gleaned from the moon will inspire a new generation of thought and action.
Without fail, every major program and mission NASA has invested in has led to technologies and capabilities that have shaped our culture.
The breakthroughs of the Artemis era will define our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the moon today are just the beginning of a lunar economy that will see hundreds of thousands of new jobs develop around the world.
This is not an ambition of one entity or one country. The exploration of the moon is a shared effort,
woven together by a desire for the greater good.
Why the moon? Because the missions of tomorrow will be sparked by the accomplishments of the Artemis generation today.
Because the ambition to go has already begun.
And because Mars is calling. We need to learn what it takes to establish community on another cosmic shore. So let's camp close before pushing out.
And so, we go to the moon now, not as a series of isolated missions, but to build a community on and around the moon capable of proving how to live on other worlds.
We'll use the lessons from more than 50 years of peaceful exploration to send a new generation to the lunar surface to stay.
We will anchor our efforts on the lunar South Pole to establish the Artemis Base Camp,
positioning us for long-term science and exploration of the lunar surface.
We will prove what it takes to assemble a complex ship in deep space.
We will perfect descending down to and returning from a distant surface.
We will learn how humans can survive and thrive in a partial gravity environment.
With improved spacesuit designs, mobile habitats, and with reconnaissance robots pre-positioning and relocating supplies.
We will learn how to utilize the resources we find on these other worlds, starting with finding water ice and purifying it to drinkable water.
And refining that into hydrogen for fuel and oxygen to breathe.
We will establish fission power plants on the surface of the moon capable of supporting a growing community of efforts.
And we will expand the logistics supply chain
to enable commercial and international partners
to resupply and refuel deep space outposts.
None of this is simple or easy, but nothing in our history ever has been.
The Eagle has landed. We got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This kind of continuous lunar presence is a natural extension of all that we've learned in low Earth orbit. And what we will accomplish there will ensure the monumental missions to Mars are within reach. As we ready the launch of the first Artemis mission, and as commercial companies ready their lunar landers for the first private payload deliveries, we have already begun to take the next step.
At NASA, we have always answered the innate call to go.
With Artemis,
We are going to stay.
Proving that humanity
Can live on the moon,
Mars,
and other worlds
And share the wonders of the solar system with all.
Our story is one of people.
All those who make this journey possible.
From advocates across communities
to companies across industries,
to countries around the world.
We achieve this collective endeavor.
Our efforts create impact for all.
Technologies that revolutionize industries.
And jobs that bring prosperity to people. The discoveries from space
benefit the way we live on Earth today.
And those from the moon
will create a better future
for generations to come.
But to do that,
we must go.
Hi, I'm Chell Ingram. My name is Raja Chari.
Kayla Barron.
Kate Rubens.
Hi, I'm Christina Cook.
NASA astronaut Joe Akaba.
Jessica Meir.
Woody Hoberg.
Ann McLean.
Stephanie Wilson.
My name is Johnny Kim.
Nicole Mann.
Victor Glover.
Jessica Watkins.
Hi, I'm Matthew Dominic.
Jasmine Mobilli.
Frank Rubio.
Scott Tingleton.
This is what we do.
This is what we will do.
Let's go.
We go to the moon to learn how to live on other planets.
For the benefit of all.
An update on our Artemis 1 moon mission, a first for our James Webb Space Telescope, and a new target launch date for the next commercial crew mission. A few of the stories to tell you about this week at NASA. Our uncrewed Artemis 1 flight test is the first integrated test of NASA's Orion spacecraft, Space Launch System or SLS, the most powerful rocket in the world, and the ground systems at the agency's Kennedy Space Center in Florida. Over the course of about 38 days, the mission will see Orion travel thousands of miles beyond the moon, farther than any spacecraft built for humans has ever flown. Artemis 1 is the first in a series of increasingly complex missions that will provide a foundation for human deep space exploration and demonstrate our commitment and capability to extend human existence to the moon and beyond. For the first time, astronomers have used our James Webb Space Telescope to take a direct image of an exoplanet. The planet, called HIP 65426b, is a gas giant about 5 to 10 times the mass of Jupiter. Taking direct images of exoplanets is challenging because stars are so much brighter than planets. But Webb has an instrument called a coronagraph that blocks out starlight and makes it possible to capture direct images of certain exoplanets. This ability could help Webb reveal more information than ever before about exoplanets. NASA and SpaceX are now targeting no earlier than 12:45 p.m. Eastern Daylight Time on October 3rd for the launch of the agency's Crew 5 mission to the International Space Station. The launch date adjustment was made to accommodate spacecraft traffic coming to and leaving from the space station. NASA astronauts Nicole Mann and Josh Cassada, Japan Aerospace Exploration Agency astronaut Koichi Wakata, and Roscosmos cosmonaut Anna Kikina will launch aboard a SpaceX Crew Dragon spacecraft from our Kennedy Space Center. NASA, the French space agency CNES, and SpaceX are now targeting December 5th for the launch of the Surface Water and Ocean Topography or SWOT satellite. SWOT is the first satellite mission that will survey nearly all water on Earth at an unprecedented level of detail. The mission will help inform water equity and water management decisions, provide new insights into Earth's water and energy cycle, and help prepare communities for rising seas and changing coastlines resulting from climate change. Engineers have fixed an issue that was affecting data from NASA's Voyager 1 spacecraft. They discovered that Voyager 1's Attitude Articulation and Control System, or AACS, a critical system aboard the probe, had been sending garbled telemetry data through an onboard computer that stopped working correctly years ago. Consequently, that computer corrupted the information. Voyager 1 and Voyager 2 are celebrating an anniversary. The twin probes, which were launched weeks apart in late August and early September of 1977, have been exploring our solar system for 45 years. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
The International Space Station, an unparalleled laboratory for cutting-edge research unachievable in Earth's gravity for the benefit of all humanity. An observatory for Earth's evolving climate. A beacon of international collaboration. And our home until 2030. As the station enters its third decade, it is busier than ever, developing technology for human exploration missions to the Moon and Mars, finding new ways to combat disease, and acting as a testbed for in-space manufacturing of advanced materials and new medical products. Humanity's future is an ever-expanding team of nations and companies enabling exploration together and for the benefit of all. The International Space Station is a critical step on a great journey ahead to the Moon and beyond.
For every generation, the Moon has been a beacon of tides and time, of dreams and destiny. For many across NASA and around the world, it has been calling to us. It has been the daily efforts of thousands whose quiet resolve has pressed us forward and prepared us for this next moment. We don't just stand on the shoulders of giants. We stand shoulder to shoulder with the generations of dreamers and doers that have navigated every phase of preparation. To every hand that has added a fingerprint to what we now call Artemis, thank you. All of your hard work will soon be realized. Today, the moment of return to the Moon has never been closer. The path forward never so clear. The number of those committed to the Artemis Accords continues to grow. The commercial lunar delivery missions that will pave the way are nearing launch. And as NASA's Artemis 1 stands fully stacked, the hardware for our future human missions to the Moon is well underway. Are there challenges ahead? Certainly. But this is our path to Mars. We are about reaching further into the unknown and learning how to live on other worlds. Because the farther we reach, the greater we grow. And as history has taught us, the greatest of these benefits are fully realized and utilized here. With the launch of Artemis 1, we say we return to the Moon for all humanity.
We are less than 2 days away from our next opportunity to launch the Space Launch System rocket and Orion spacecraft on a flight test beyond the moon. Welcome to NASA's status briefing for Artemis 1. I'm Rachel Kraft with NASA's Office of Communications. The mission management team met earlier today to review the status of preparations for the mission. Launch of the uncrewed Artemis 1 flight test is currently targeted for Saturday, September 3rd at 2:17 p.m. with a 2-hour launch window. Joining us here at Kennedy Space Center in Florida, we have several guests who will give us an update on the preparations and overall status. We have Mike Serafin, Artemis 1 Mission Manager, John Honeycutt, SLS Program Manager, John Blevins, SLS Chief Engineer, Charlie Blackwell Thompson, Artemis Launch Director, and Melody Levin, Weather Officer with the Space Launch Delta 45th. We'll start with a few comments from our guests, and then we'll take questions. For those of you joining on the phone, you can press *1 to be entered into the question queue. And I will also note, we do want to keep our briefing to an hour today to give our guests some much needed rest. So with that, Mike, let's start with you.
Okay, well, good afternoon, and thank you for continuing to follow the Artemis 1 mission. If you recall, 2 days ago, we had a scrub following the August 29th launch attempt, and we needed a little bit of time to assess our risk posture headed into a subsequent launch attempt. And we reviewed that today as a mission management team. A little bit of time helped us work through all of the information that we gathered from the first launch attempt. And we worked through a number of issues, and we discussed our risk acceptance rationale for a subsequent launch attempt. If you recall from our prior attempt, we had the tail service mast umbilical leak. We had a hydrogen leak in the tail service mast umbilical. That coming out of the last launch attempt, we met and agreed to do some work out at the launch pad. That work has been completed. We had an issue with the core stage intertank vent valve. That has checked out, and we do not consider that to be an issue. We also had an issue confirming that we were able to thermally condition all of the core stage engines within the required temperature limits as part of what we call the engine bleed. And we worked through that today. And then near the end of the launch attempt, we saw some cracks in the foam on the thermal protection system on the core stage at the intertank flange, and we reviewed that issue today. There was some incremental risk acceptance. As the mission management team, it is our role to review risk acceptance and then the flight readiness rationale. And then we also have requirements change authority following the agency flight readiness review, and we review any changes from the previously accepted risk baseline that we had at the agency FRR. And we did that today. Only 2 of those items required some incremental risk acceptance, and that was the thermal conditioning of the engines associated with the engine bleed, and then the core stage thermal protection system, the crack that we saw, specifically what is termed crack number 2 at the intertank flange, just due to the potential for debris transport, and then contact with the booster SEP motor. It's a low likelihood occurrence, but it is something that we considered an acceptable risk. So we reviewed our risk acceptance rationale and our overall risk posture, and we are setting up for a launch attempt on September the 3rd, Saturday, and we're comfortable with our flight rationale and risk acceptance there. In addition to that, we did have some late analysis come in associated with an off-nominal performance scenario where if we have, and this we're not planning on this, but should we have a underspeed at the completion of the translunar injection maneuver, it shows that our trajectory would put us into what we call an eclipse violation, which is a power production issue for the Orion spacecraft. So as a result of that, it is specific to the September 4th launch opportunity. We agreed to take that off the plate. So we are, again, proceeding into our Saturday launch attempt. We're comfortable with our risk posture. That said, there's no guarantee that we're going to get off on Saturday, but we're going to try. And the technical teams have put in a tremendous amount of work in a very short amount of time to get us here. And again, thanks to the work and the effort that they've put in. So with that, I'll pass it back to you, Rachel.
Okay. John Honeycutt.
Yeah, good afternoon. It's a pleasure to be here. I think when I talked day before yesterday, I mentioned that we had a lot of data to go look at. And so we had come out of the first launch attempt. We were unsuccessful on gathering the data that we wanted to gather for that, what we call the bleed kickstart. The team has done a tremendous amount of work starting right after the launch, even up until this morning and to the noon hour, leading us into the MMT meeting. What I would tell you is they just did an outstanding job nailing it flat, and we'll share some more of those technical details. But at a high level, we have convinced ourselves without a shadow of a doubt that we have good quality liquid hydrogen going through the engines, and there's no fuzz on that. We've also, through the course of analyzing the data, looked at 5 additional measurements that we can look at to assure ourselves that we are getting that quality data. And that's on the engine. That's on the engine side, and then on the core stage side, we were able to go back and verify that the core stage is providing the amount of hydrogen and the quality of hydrogen to all 4 engines. And so I'll turn it. I say Dr. Blevins and his technical team just did an outstanding job working through that, and we'll share some of those details, I'm sure, as we get to the questions.
Okay. John Blevins.
Yeah, I'll just add that we do have an outstanding team, and they did look at the data. We had some things we were looking for in launch attempt 1 that were combined with what we expected to do in a wet dress. And so we had some sensors that didn't tell us what we thought we would do, and we did the right thing by standing down with that uncertainty on Monday. But we have confirmed that we did have good flow through those engines. We know we can chill those engines. We're ready to proceed that way to launch. The SLS team does a lot of other things, and as Mike mentioned, we brought some other things. We inspect the vehicle. We brought the concerns we had over any TPS as minimal as they are forward, and we've analyzed, and the teams are ready to support launch attempts on Saturday.
Okay, thank you. Charlie?
Well, good evening, everyone. It's great to be back here talking to you about our preparations for Launch Countdown. I think we met and talked just a couple days ago, and when we had our last press conference on Tuesday, we had finished up our safing and securing out at the pad, and we were getting ready to send the access stand out so that we could begin work on the LH2 TSMU purge can, where we detected that leak during our tanking operations. That work is all behind us. We finished up the work. We were able to find what we believe is the source of the leak and correct that. And that purge can's been put back together. We have leak tested it at ambient conditions and also done some flow-through tests with our HAS-gas system, and we believe we're in a good configuration for the next loading attempt. We also went back based on what we saw during and working with John's team, looking at any countdown enhancements that we might need to make. We have made a couple of changes as we prepare for this next loading operation. And really what that means is that we're going to start our LH2 chill down, the facility side of the chill down, right around the same time that we begin our LOX chill down. So that'll allow us to begin that kickstart bleed a little bit earlier, and we'll pick up that kickstart because I know I'll probably get a question about when that is, and we'll start that just about 8 o'clock on Saturday morning. So we made a couple of changes to the countdown. Our teams have been very busy in Firing Room 3, running against the model. We finished up 2 days of that testing to make sure that we had our procedures all down and ready to go. It didn't require any software changes. It was just the procedures that we go through, but we also want to make sure that we have those ready to go. And everything right now is on track. We have remained in launch countdown. I know some folks think that, launch countdown, it starts 2 days prior. Sometimes when we're in a scrub, we stay in launch countdown. And that's what we have done this particular time. We've been originally in a 96-hour scrub. Of course, we added a day on to go do this purge can work. And we've also taken replenishment of both LOX and hydrogen. Both tanks are topped off, which is great. And so we are on track to support our 0557 tanking operations on Saturday morning, setting us up, as Mike said, for that 217 window open.
Okay, thank you. And Melody.
All right, good evening, everyone. You got to me a little faster than I thought. Anyway, as I was walking over here, I noticed a lot of Anvils kind of streaming in from the West Coast, and I even saw some Mattis clouds out there. So let's go ahead and look at satellite and see what's going on. So basically, right now, we actually do have offshore flow, meaning flow out of the west coast, or generally a westerly flow. And you can see a lot of thunderstorms popping up across the interior portion of the state at this point in time. They are spreading east, but I actually just looked at radar. You're looking at infrared satellite here. Radar is different. But in general, the showers themselves are staying across the interior portion, not getting close to the Cape at this point in time, but you can see a lot of Anvil from a lot of those showers and thunderstorms. But anyway, this pattern that we have today is actually going to be transitioning into more of an onshore flow regime as we get into tomorrow, and that is mainly due to the fact that we'll have a ridge that's building across the state of Florida. And what it will do is deliver easterly flow, and that easterly flow will stay intact for several days. So that's actually normally pretty good news for us. It keeps our lightning risk a little bit lower than what we would normally see on a typical afternoon in the summer for Florida. So anyway, we'll move on to the primary launch window forecast. And with that, you can see I have a 60% go for the launch window when it opens up in the early afternoon on Saturday. Winds pretty steady out of the east at 8 to 12 knots, which if you want to convert to miles per hour, that is 9 to 13 miles per hour. I know there's some weather nerds out there that might pick up on that. But anyway, temperature pretty warm, as you can expect. It is Florida, 86 degrees. Our main concerns for the primary launch window will be the cumulus cloud rule and the surface electric field rule. So then we'll go ahead and skip ahead to the backup window, which is actually Monday. And that actually improves. The weather improves a little bit to 70%. And that's mainly due to the fact that the launch window is a little bit later into the afternoon time frames. And with that, we would expect the East Coast sea breeze to be positioned farther across the interior portion of the state, giving us a lot of sinking air behind it in general. So basically, the weather looks good. I wouldn't be shocked if there are periods where we are technically red for weather. But the bottom line is that I don't expect weather to be a showstopper for either launch window. So with that, I'll go ahead and pass it back.
Okay, thanks very much. We will take some questions now. We'll take some questions in the room and on the phone line. A reminder to reporters to please limit to one question. And if you will state your name, affiliation, and who you're addressing your question, that would be a big help. So we'll start with Marcia Dunn.
Marcia Dunn, Associated Press for either of the Johns. It sounds like a bad sensor then. Is that your best hunch? And could it be anything else besides a bad sensor for the Monday's situation? And what would happen to an engine if the fuel wasn't cold enough at ignition? Would it just crack? Would it burst? Something else? Okay.
Yeah, I can start and then I'll let Dr. Blevins add in. Yes, we do think we know we had a bad sensor. That was our challenge early in the week, where we could not make the physics of the system line up to what we were seeing with that one sensor. So since then, we've had time to go back and look at the data and compare many sources of data and do some independent analysis that confirmed it's a bad sensor and we're getting good quality propellant through the engine. And so your question on the engine is, there's a lot of things that we do on the engine to monitor the engine to make sure that it's operating the way we want to see it, through operational flight instrumentation, as well as we have what we call an advanced health monitoring system that is on each engine that is designed primarily to look at vibrations and that sort of thing on the engine and pick those up as an early warning. And so, John, I'll let you add more there.
Yeah, let me follow up. The problem in part with the sensor is during ranges of temperature, it gave us the right slopes. It seemed to work fine, and then it did not give us an indication that we expected at the very cold temperature. So it really was an interesting signal, and that's part of the pause. It didn't just fail off scale or anything. So, but John is right. It is conclusive that sensor was not a witness for what we were looking for. It's absolutely true. On the engine side, we do have advanced health monitoring. The reason we chill the engines for numerous reasons, but the primary one is for the high pressure turbopump bearing. And that high pressure turbopump bearing doesn't have to be all the way as cold as the liquid, but it's got to be cold. And if we know the liquid is going through, then we know it's about that temperature, and that gives us margin to that problem. And if it starts up and it's not cold, then it can skid. Ultimately, that causes excess wear on startup. That would manifest potentially as a shutdown during flight. It would be a red line. It wouldn't be, I'm not sure how you characterized it, but it wouldn't be an uncontained failure generally for that particular issue. I mean, but as John said, we have advanced health monitoring on the engines for a reason. These are high performance, really the highest horsepower per mass device that has ever been built. And so we need that health monitoring, and there's numerous things that we're looking for when we do that. So, but the sensor was bad. And in this case, what we're protecting against is a bearing skidding on startup and causing excessive wear.
Bill Harwood.
Yeah, hi, Bill Harwood, CBS. One question, Rachel, but it's got 2 or 3 parts, so sorry about that. No, it's pretty straightforward. What gets masked? I'm assuming you have to mask out the suspect sensor, but where in the software do you tell it this is okay to start an engine, this is not okay to start the engine, and where would that occur? Is that before terminal count, or would it be at ALS transition? How does that work? And what, I guess another way of asking that question is, what tells the computers that the engines are at the right temperature to start? I mean, how is it knowing it's at that 420 degrees John mentioned yesterday to be able to press ahead with start?
I'll go ahead and take this one. So first of all, the protection for the engine is not, this sensor was never intended to be used as an LCC or for this purpose. It is not part of ALS. It is not part of the startup protection. Ultimately, the reason we use this sensor is to get an initial indication of cold fluid. We did combine this launch attempt 1 with an objective we did not achieve in wet dress, and that's why we had more verification work to do. And we were going to do that verification early in launch attempt 1. This sensor failure prevented that verification, and that's why we had to go to subsequent measurements. And we were able to achieve that really only because we were in these conditions for a long time with fully tanked and flow through the engines. If we wouldn't have done that, we wouldn't be able to verify all that we could to verify that it was liquid and that was a bad sensor. But ultimately, the protection for the engine that's in ALS are temperatures and pressures, but they're not the ones that we use for a long chill of the engine. If you reflect on the last answer, it was that, we're trying to chill the engine to get a bearing cold that we don't measure. And so that's buried inside of part of the engine. And so we count on a certain amount of mass flow for a certain amount of time in order to ensure that that bearing is cold. We did that during shuttle. We've done that during the entire program that used formerly the Space Shuttle main engines and now the RS-25s. And so that verification is a process verification we just didn't achieve in WDR4. That's why we were using this measurement. It's not part of ALS, so there's no masking in the computer software. All the normal protections are in place. We added an LCC. I asked Charlie to add an LCC for this verification because we just didn't receive it in WDR4. That's ultimately what this measurement is. It was never really intended for the purpose we ended up using it for.
So temps during chill down wouldn't play into whether or not to start an engine. There are what
No,
they are.
there are other temperatures that verify the liquid at the interface to the turbopumps that were ready to go and other skin temps. This one was used as a witness for the bearing chilling for a certain amount of time and is not strictly relevant to the startup conditions.
Yeah, and John mentioned something that I want to pile on a little bit on. It's he talked about what we learned in the shuttle, and we did this engine conditioning through process control. And so I think I'd gotten a question about the difference between shuttle and SLS earlier in the week, and we had those recirculation pumps on the shuttle where we took that warm. We took the heat out of the engine by circulating the hydrogen through the engine and carrying it back into the hydrogen tank to boil off. And so we're in the same situation here where we want to use our process control to assure ourselves that we're delivering the propellant quality that we need to the engines. And so, we had that process control on shuttle for these engines. It worked fine. We validated that process control when we were at Stennis for the green run. And our plan was on Monday to validate that for this vehicle with the configuration that we have on the launch pad. I talked to you relative to the differences between Stennis early in the week and the launch and what we have out at the launch pad. All those are still in the direction of goodness. We've got a bigger vent line on the ground side. It's insulated, which means we could flow more through that line. And our bleed system and our relief system is bigger than we had at Stennis. So all that still holds true.
Okay, we'll do stick with the front row here with Stephen.
Stephen Young with Spaceflight Now for Charlie. We're so used to seeing views inside the LCC, and on Monday we saw nothing, and your team was working so hard, and there's so much interest in this mission. I'm wondering, why are we not seeing any video in our isolated feeds or on NASA TV from inside the firing room?
Yeah, there will be views from the firing room that will be mixed in with all of the coverage.
Okay, Marcia Smith.
Marcia Smith, spacepolicyonline.com. I'm curious what the other limiting factors are and how many times you can attempt to launch. You have the flight termination system battery that you have to come back to the VAB to swap that out. Are there other limiting factors? How many times can you tank and detank? How many times can you give this a shot?
Yeah, I'll take a first crack at that one. Physics is one of the key limiting factors associated with the sun. The Earth and the Moon position relative to what this initial configuration of the Space Launch System rocket is capable of with the interim cryo propulsion stage. So we lose our ability to fly into a lunar intercept after September the 6th. And that's one of the key limiters. There's also the flight termination system. It's essentially a reliability check in the interest of public safety. And I don't know, Charlie, if you have any others to add on that, but those are kind of the key drivers at this point.
So you can tank and detank an infinite number of times?
Not infinitely. We track those, and we're a ways away from those limits.
Okay, Stephen, and then we'll go to Irene.
Stephen Clark, Spaceflight Now. Just so I understand, on WDR4 back on the 20th of June, ALS cut the countdown at 29 seconds for when it realized the engines were not thermally conditioned for flight. If the engines are not at the proper temperature on Monday, the sensor notwithstanding, ALS would still cut the count. There's no risk of igniting an engine at the wrong temperature. Is that a proper understanding?
Yeah, that's correct. I want to make sure you understand. ALS is checking the temperature, pressure, and many other parameters at that moment. The whole point of the sensor that we use, which we would have just verified process, as John talked about, is to get time at temperature for that one part. And now we've confirmed that through other means. So the engine will not start unless we hit the engine start box. ALS will shut it down.
And are you actually masking that?
No,
sensor?
we are not masking anything in ALS. No, we're not masking what we're measuring. That sensor is an engineering sensor for engineering data. It is not a flight. It's not OFI. It's not a flight instrument.
Okay, and we'll go to the second row to Irene Klotz, and then we'll take a few from the phone.
Thanks. Irene Klotz with Aviation Week, maybe for whomever. Do you think that starting the kickstart procedure early will give you a reading that the sensor is now working, even though it's just an engineering sensor? And do you think that just because they're engineering sensors and not the fidelity that you have elsewhere in the system and in the ALS software, that that's why the other engines were not quite cold enough either?
Yeah, let me take that. No matter what that sensor does, I've learned a lot about the flow process, which is what you do a WDR for, and we ended up unfortunately doing that somewhat on Monday. And we stayed at condition for a while, and we flowed not just through all four engines, but even through just the one that we were slightly more concerned about. And so whatever that sensor does, I have lots of supporting evidence that's much higher fidelity from the engine itself on that chill process. Starting it earlier certainly makes me happy because I'll get an indication earlier in the day that the engine's looking good. And time at temperature, as I told you, is what achieves a good bearing temperature, so we'll do that. As far as the other three temperatures, they're extremely consistent with saturated liquid temperatures. And, I think a lot of people have talked about those temperatures being off. In the case of Stennis, we had those three temperatures, and we defined what saturation was by what we measured at Stennis because we knew we had saturated liquid in the core stage green run. And in this case, if you're able to go back and take a look at that data, you'll see that they were at saturation temperature. So they may have been 1 to 2 degrees Rankine away from what we expected or what we saw as a witness prior 18 months earlier at the core stage green run, but they are consistent with saturated liquid. So there's no question that the engines receive saturated liquid. And quite honestly, normally, you would have done a WDR and you would have a few weeks to review that data, and there wouldn't have been that comment about it not reading on all these sensors and that kind of thing. We would have used all the evidence, and we've compressed that time, and we've got very good evidence, as John has said, that there's no question that we had liquid flow through that engine. And now we have other witnesses, and we'll use the data we have available when we do the kickstart procedure, and we've got lots of data in order to confirm that we start that liquid flow process.
Thanks. Okay, and we'll go to the phone and take a few questions from there. We'll start with Michael Sheets of CNBC.
Hi, everybody. I believe my question is for Mike Serafin, but it's most specific to the amount of risk analysis you're looking at for a Saturday launch attempt. Based on the data that you've seen so far, given that this is supposed to be a full demonstration of the system, if there were astronauts flying on board this mission, would you still be launching based on the parameters that you're looking at, or are the risk analysis that you're considering different than if you were, launching the Artemis 2 mission?
Yeah, Michael, that's not an easy question to answer because again, Artemis 1 is the first test flight in a series of increasingly complex missions, and the next mission is intentionally Artemis 2 is intentionally our crewed flight test. So Artemis 1, we are buying down the risk associated with crewed flight on the next mission, specifically reentry of the vehicle at lunar reentry conditions. In order to get there, we have to set up those initial conditions using the performance of the rocket by getting it to the lunar reentry conditions. The rocket has to deliver us to the point of translunar injection. We want to shake down the spacecraft through flying out through the Van Allen radiation belts, the orbital debris field, and operate it in the deep space environment. Those are all things that we have to do with crew on board on the very next mission. And we know that there's risk involved with this first mission, but in terms of the incremental risks that we dispositioned today at the mission management team, it was a marginal increase in risk, and we are clearly ready to fly on Saturday with an understanding of what that risk is. We would have a very similar discussion on Artemis 2 if we had any of the conditions that we're seeing on this flight, and we would make an appropriate decision. So it's a hard question to answer because it presumes that we are successful on Artemis 1, and there's a non-zero chance that we will find something on Artemis 1 that will cause us to reassess our risk posture on a crewed flight.
We'll stick with questions on the phone, and we'll take our next question from Lauren Grush with Bloomberg.
Hi, thank you for taking my question. So correct me if I'm wrong, but it sounds like the sensor that caused all the drama is separate from the critical sensors and other data inputs the engine computers use to know that they're in the right launch configuration. So why do you need that sensor at all? And was there an option during the countdown to cross-check against those engine sensors and inputs? Or are you saying that there wasn't enough time to do that? Thanks.
Yeah, that's a good question. We do not need this sensor for flight. The sensor was set up to be engineering information for a chill down confirmation process. And what we're trying to do is make sure that we have cold liquid for a certain amount of time, just like we did on shuttle, to infer that the rest of the hardware is cold. And that's what we're trying to do, is just chill that down. That's why we call it the chill process. This sensor is not used for that time. Those sensors were deadheaded that you would use at that particular time and were not appropriate references for us. In fact, that's not what we're using to confirm that we had liquid flow through the engine per se. And so, that it was an engineering analysis where we combined the wet dress with the launch attempt, and we were unable to confirm that chill process, and that's what stopped us.
Yeah, and John, let me add a point here. We had a plan going into the August 29th launch attempt, and it used these sensors to help confirm the proper thermal conditioning of the engines. We had trained that plan, and then we ran into other issues. We ran into a leak at the tail service mast umbilical, and then we had a vent valve that was not operating properly. So we were off the script in terms of the normal tanking operation, and the team did a fantastic job working through the managing of a hazardous condition. And one of the worst things that you can do when you find yourself in a hazardous condition is just go even further off script and to deviate and get into an operation that you're not prepared or trained for. So the team did absolutely the right thing on the 29th, and they knocked off the operation, and they knocked off the test, and they got us into a safe configuration. And then they spent the last couple of days reviewing the data, and that was absolutely the right thing to go do. 2020 hindsight, these particular sensors we know aren't the best cue to work off of, and we've reassessed the plan, and we have a great plan moving forward. We understand the risk posture associated with getting the engines thermally conditioned, and the team was asked today very specifically, are you ready to go load the vehicle with this earlier tanking and earlier bleed flow operation? And the answer was absolutely yes. So I don't know, Charlie, if you have anything to add to that one.
No, I think you covered it.
Okay. Our next question is from Eric Berger with Ars Technica.
Hi, thanks for doing this. That was great, Mike. Thank you. I'd like to take another crack at a question I think Marcia was trying to ask earlier. Based upon comments we've heard during earlier briefings, it does seem like there's been some mild concern about the shelf life of the stacked Artemis 1 rocket. And I guess what I'd like to understand is, are there wear and tear issues that you've mentioned on the rocket? Marcia asked how many cycles were left in the core stage propellant tanks, and just wondering, like, are you feeling some urgency to get this rocket off in the next month or two, or are you good in the configuration you're in now for quite a while? Thank you.
We're good in the configuration we're in for a while. As I alluded to earlier, I'm not going to give you an exact number, but I know we're well into the high double digits on additional tank cycles. As far as worrying about things with the rocket sitting on the pad, there are probably more little things like we see cracks in TPS and that sort of thing that we have to go analyze to clear. But the big thing we want to avoid is rollbacks to the VAB. Those are the things that Dr. Blevins has told me will put more stress on the vehicle than anything else. Now, that said, we've still got rolls left in the vehicle, but we want to watch that and manage it. Do you want to add anything, John?
I'll say we track all life limited items. We watch that very closely. I don't have any concern on the pressure cycles of the tank, just as you said, John. We have numerous cycles left, and that's to a good margin of safety. I do like to protect the rolls because they're complicated and they affect every part of the rocket, but we have plenty of rolls left at this time too.
Okay, one more on the phone and then we'll come back in the room. Joey Roulette with Reuters.
Hey, thanks. My question was asked.
Okay, we'll come back in here in the room. We'll go there in the second row, Jeff Faust.
Jeff Faust, Space News. For Mike Seraphin, quick question. If we do launch on Saturday, what is the length of the mission? And do you have to do any changes to the mission plan if it's shorter than 42 days?
Yeah, Jeff, that's a great question. I will confirm it here, but I believe it's a 37-day mission with the splashdown on October the 11th. In terms of changes to work, obviously, you launch a day later, you have to schedule your satellite coverage and your deep space network coverage. You have to issue a whole host of notifications, and some of those are to aircraft that are going to be taking observations of the vehicle during launch or during splashdown. We've notified the Navy that's providing our recovery assets. We've notified the FAA via the Eastern Range for notice to air missions. We've notified the Coast Guard for notice to mariners for any boats that are out there, for the splashdown locations of any of the jettisoned items, but also of the end of mission location. So there's a whole host of things that the team works through to replan, and all of those notifications, but also products have been pre-planned ahead of the mission, and the team has pulled those off the shelf. They're putting the final touches on a lot of those things, and the process is flexible enough to handle that. So we're not concerned with any of those items.
Okay, we'll come back here in the front row and then we'll move over to the other side. Right here, yep.
Chris Gephardt with NASA Spaceflight. I think these are both for Charlie. How many cutouts and colas do we have for Saturday's window? What's the longest one within there? And starting LH2 chill down on the ground side a bit early, starting to bleed a bit early, that sounds to me like you're going to lose a little bit more to boil off and a little bit more to bleed. Where does that leave you on the LH2 margins for the day? I know you have to top off the tank afterward, but like on launch day, where does that leave you for the 2-hour window?
Let's see. I'll start with the colas and cutouts. So I probably have a report that's in my email. We get those at L-2 day. So I haven't looked at it specific to our next opportunity, but I can tell you that for our previous opportunity, we had somewhere in the neighborhood of about 30 to 40 cutouts. So it's a fairly significant number. Most of them are really short, just a couple of seconds long. We did have a couple that were a little bit longer, maybe on the order of a minute or so. But I can absolutely get you a specific number. And then let's see, what was the second part?
So starting the LH2 chill down in the bleed. Yeah.
Starting it earlier. So we went off and analyzed that. You're absolutely correct. If you start it earlier and you start the bleed earlier, you're going to consume more. And we did go off and look at that, did the analysis. We will be able to support the entirety of the window, but we will have a little less margin in the tank when we're done.
Okay, thank you. We'll go here next.
This question is for Mike Murphy. My name is Ada Monzon, Guapa TV, Puerto Rico. Can you elaborate on the plan of next launch windows? Even if it's not next Monday, then what are the choices or the opportunities even by the end of the month or by October?
Yeah, it's a great question. And for Jeff, I did verify that October 11th is our splashdown date, and it's a 37-day mission. So in terms of mission availability, we do have a reservation with the range for September 5th. So if we do not launch on Saturday, we'll be looking at a afternoon launch on the 5th. The 6th is in play. It's a fairly short launch window on the 6th of September. Should we not tank on the 5th, we may elect to move to the 6th. Once we get past the 6th of September, September the 19th is the earliest from a physics-based standpoint that we could pick it up. And then that launch period ends on October the 4th. Obviously, we would need to account for when did we roll back to the vehicle assembly building and what that looks like relative to where could we pick it up. We would also have to assess, why did we roll back to the vehicle assembly building? Did we just simply not get lucky with weather and we had to roll back and check out the flight termination system again? Or was it a technical issue that requires access to a very specific part of the rocket? We would have to look at how long does it take to gain access, the availability of spare parts, or any reason that we would have rolled back. So there's a whole host of variables in there, but that gives you a sense of kind of the relative time frame.
Okay, let's come to the other side of the room here. We'll go to Ken Kramer.
Hi, thank you. Ken Kramer, Space Up Close. For Charlie Blackwell Thompson, please, can you talk a little bit more about the liquid hydrogen work you did on the purge can? How did you discover it? What did you do to fix it? And how do you determine it was fixed? Thank you.
So, after WDR3, we also had a leak in the purge can. And while you never want to have a leak, it did give us an opportunity to really do a very close examination of what caused that leak. And so we learned a lot from that. And we learned what are all the things that you want to go check. And we took some very specific actions after WDR3. You may recall we were setting up very similar to what we did over the last day or so out at the pad. We were getting the access in place, and then we made a decision to roll back because we wanted to go allow the GN2 production plant to make the upgrades. And so we went back to the VAB and opened up the purge can. We looked at all of the penetrations that go into that can, the soft goods associated with it, looked at the gaskets, looked at the flanges, checked all the torques, and found that there was some relaxation in the torques on the flange. And we ended up retorquing them. We made a couple of changes to the drain assist purge. You may remember seeing the pictures. It was kind of a cantilevered, arrangement into the back of the can, so it kind of put a load on there. We ended up changing that. And anyway, we came back out for WDR4. We saw good performance. In the purge can, we obviously picked up the 4-inch QD leak, so that presented a different challenge for the team to go take on. But what we saw during launch attempt 1 is we saw a similar signature. We had hydrogen concentration increasing. It was fine during slow fill. It was as we got into the higher pressures and saw more flow across that interface. We were able to manage our way through it. The team was able to vary the flow rates and stay within the specifications. But certainly we saw it reoccur during drain and recognized that we needed to go take a closer look at what was causing this. So as I said, we went back into the purge can out at the pad because we'd had the opportunity after WDR3 to come up with, here's the 3 or 4 or 5 things you need to go look at. We went and checked all those same things again. And what we found is in that 8-inch, in the purge can and in the 8-inch QD, there is a pressure sense line there. It's a penetration into the can and into the 8-inch there. And what happened is we found that loose. And we believe, we found that loose. So we changed out the seal around that pressure sense line. We retorqued it, and we believe that that is most likely the leak source. We checked the flange, the torques on the flange, everything was nominal. We did an inspection of the gasket. It was nominal, and we checked every other fitting there, and everything was found to be nominal. So finding that one item loose, we feel that that's most likely the cause. Now, as we've talked before, we did ambient leak checks, and afterwards, after we put it all back together, and we didn't find anything, but until you hit it with cryo, you really don't know for sure. So.
Do you know why it was loose?
No, I mean, I have to believe that it was something that's happened between when it was checked in the VAB and at the pad. So it could be from roll or from something else, but no, I don't know for certain what caused it to become loose.
Okay, we'll take here in the black shirt.
Hi, Michael Grushko, National Geographic. This is for Mike Serafin. Following up on Michael Sheets' question earlier. Earlier in the week, you gave an assessment that there was a 1 in 125 risk of loss of Orion based on all phases of flight. Now you've added 2 incremental risk acceptances to the mix, the foam and then the engine conditioning. Do you have an updated number? And if so, what is it?
We don't have an updated number. What I would say is there was no appreciable increase in risk. There was a delta risk acceptance because we know we have a crack in the foam. We have a non-conformance at the intertank flange area. We know its location. We know the approximate size, and there's a small likelihood that it could be liberated during launch, follow a very specific trajectory, and hit one specific location on a booster that could cause a problem. The likelihood of that is very low. In addition to that, as we talked with the engine bleed, the thermal conditioning, it really comes down to the fact that we haven't demonstrated it previously. We have a high confidence that we can get through this, given the indications that Dr. Blevins and John Honeycutt talked earlier. The team has more insight given where we are. We've trained it. We have
have an issue with the vent valve. The vent valve is in the system where we had the leak. So the vent valve was inside of the inner tank. it goes to the inner tank structure, and then there's an umbilical there that vents out to the ground. And so the team saw the leak there. So it's probably better for Charlie to answer that one.
Yeah, so I think John described it really well. So this is part of the hydrogen tank vent system, goes out the umbilical arm, very similar to when we talk about the TSMU, right? There's a ground side and a flight side plate there, and the leak that we picked up was in that particular cavity. What we believe happened is as we have seen with QDs or quick disconnects before, is when you change the environment on them very rapidly, sometimes you will see a shift in the seal. That's actually one of our troubleshooting steps that we do when we see a leak is we'll let the QD warm up, and then we will allow flow back across it to see if we can get it to seat. So what had happened in the particular situation that we saw with that is we had gone all the way through our loading. Everything was fine. We had nominal performance in that QD cavity, no issues at all. But when we got into the troubleshooting of the bleed issue, that QD warmed up. We had not had, we'd had the vent valve closed, so you're not really venting through that area, and you got it warmed up for quite an amount of time. And then when we opened it and we exposed it to a very rapid change in environment, both temperature and pressure, that's when we picked up the leak there. And as a matter of course, as we went through the drain operations a little bit later, and you saw, the QD chill down, you actually saw nominal, the leak kind of sealed itself. So that's why we have confidence going into our next tanking operation. Again, we've seen this in the past where you've had rapid change in temperature and pressure. Sometimes you'll see some change in the seal, and that's what we believe caused the issue that we had on our launch temp 1.
Okay, we'll take a few from the phone. We'll go to Marina Corin with The Atlantic.
Hi, I'm Marina Corin with The Atlantic. A question for Mike Serafin. A few days before the first launch attempt, you said that if you couldn't successfully demonstrate the thermal conditioning of the engines, you wouldn't be launching that day. Now that you're confident that you'll be able to do that on Saturday, what else is on the table, something of a similar nature that you haven't tested yet that you can say today could be another showstopper?
That's a good question, Marina. Certainly, we have nearly 500 launch commit criteria and 489 launch commit criteria. Any one of which affects our overall risk posture headed into the launch attempt. So this was one particular situation that coming out the engine thermal conditioning was one particular and very unique situation that we carried out of the agency flight readiness review as a known first-time demonstration in the launch countdown. Unlike the other launch commit criteria, we just knew that this was something that we had to do successfully for the first time. The other launch commit criteria, obviously we've got to meet those or we get into elevated risk acceptance, and we do reserve the right to do that, but it would have to have adequate flight rationale. So, things like weather and a whole host of other criteria are part of our launch commit. So we will wait and see what the conditions are, and we will go when the vehicle is ready and we understand the risk posture.
Okay, we'll take another from the phone. We'll go to Ramin Skiba with Wired.
Hi, thank you. My question was answered, but I'll ask something else. I guess this is for Mike Serafin. I was just curious, will the Vice President or any Congress members or celebrity guests be in attendance on Saturday?
Obviously, Artemis 1 and this initial launch of the Space Launch System rocket and the Orion spacecraft around the moon is gathering and garnering a lot of attention nationally and internationally. We will have VIPs here. I don't have specifics on who the VIPs will be, but I would be surprised if there were not congressional stakeholders here.
Okay, and we'll come back to the room here. We'll go here in the hat.
Kristen Fisher with CNN. I've got one more question about the bad sensors. So I think this is for one of the Johns, but I just want to try to simplify it a little bit. Given that you have confirmed that this is a bad sensor now, is part of the plan, is part of the risk posture for this second launch attempt to simply ignore it?
Yeah, let me answer that. It's not a risk posture per se, because what we always wanted to do is confirm that we could get liquid in for a certain amount of time to chill the engine, and now we've confirmed that. So we weren't going to use this instrument for that purpose once we confirmed it, and now we've confirmed it. So I don't know, to me, if I would call that an increased risk posture going into launch. I think the risk that remains is that we haven't gotten to our first launch of the program yet.
I guess what about ignoring it?
What's the risk in ignoring that sensor?
Is part of the plan, is one of the things that you all could do on launch day is just to ignore the sensor, the bad sensor. Would you just ignore it?
Yes, we will.
Okay. Thank you.
Yeah.
Okay, we'll go in the next row back.
Manuel Masanti from Debate. So if you can ignore that sensor, can you ignore the other three? So you have three, you have one sensor per engine, right?
Yeah, there are three more
So
sensors.
can you ignore the four of them?
We use those to make sure the initial flow looks cold, and we're going to try to take a look at that. We have other witnesses, and we know those witnesses well now that we've done this test. And so, I won't say that we're ignoring them, but I will say that we have witnesses. What Charlie's doing for the engines is early in the count, and we will have sufficient time to verify we've got good liquid in the engines, regardless of what any of those sensors do.
Thank you. With that, I'd like to thank everyone for joining us today. We will have another pre-launch status briefing tomorrow morning at 9 a.m. Eastern. And our coverage of tanking operations starts on NASA TV Saturday at 5:45 a.m. Eastern, with our full launch coverage starting at 12:15 p.m. and our Spanish language coverage starts at 1 p.m. You can find more on our coverage plans and on the mission at nasa.gov/Artemis.
Three, two, one. Ignition. And liftoff.
Copy, 1 Alpha.
Vehicle pushing downrange. Trajectory nominal.
We are about 29 hours until our earliest opportunity to launch our Space Launch System and Orion spacecraft. You see them live there on Launch Pad 39B here at Kennedy Space Center. When it launches, Artemis 1 will be humanity's return to the moon in almost 50 years. Good morning and welcome back for another live briefing of our Artemis 1 mission. I'm Megan Cruz, and thank you so much for being here with us today. This briefing is to update you all on how our countdown is going so far. As you know, the 2-hour launch window opens tomorrow, September 3rd at 2:17 p.m. Eastern Time. Here to take your questions today are Jeremy Parsons, Deputy Manager of Exploration Ground Systems here at Kennedy. And then we also again have Melody Levin, a Launch Weather Officer with the U.S. Space Force. Good morning to you both. We will take opening remarks. Jeremy, let's start with you.
Good morning, and really appreciate everyone coming out today. Team is doing an absolutely tremendous job moving through Launch Countdown. And so yesterday at 14:17 local time, we reset the clock to T-minus 45 hours and counting. And so far, they're proceeding right on schedule. Last night, after the briefing, we powered up Orion. We performed all the RF testing. We also powered up the core stage. All looked nominal. We ran final leak checks on the inner tank umbilical. So this was the area that had a leak during Launch Countdown Event 1. Again, all passed ambient along with the tail service mast umbilicals. So good leak checks there. And then yesterday evening, we also completed removing access stands,